If ancient ruins could surprise us, they already have. Again and again, archaeologists have arrived at a site believing they understood what they were looking at, only to discover something completely unexpected beneath it, inside it, or around it. A temple turns out to be built on top of an older temple. A famous monument hides unexplored chambers. A forgotten city emerges where maps insisted nothing existed. These moments reveal an uncomfortable truth. The ancient world is often stranger than our explanations of it. Every generation inherits a version of history that feels complete, only for new discoveries to expose how much remains unknown. And perhaps that is the real mystery. Not whether secrets still exist, but how many are still waiting in places we think we already understand. Located in Multan, southern Pakistan, the tomb of Shah Rukn-e-Alam stands in a city that has been inhabited for thousands of years and once served as one of the most important crossroads of trade, religion, and knowledge in South Asia. Rising nearly 35 meters above the surrounding landscape, the massive octagonal mausoleum has dominated the skyline for more than 7 centuries. At first glance, it appears to be another medieval Islamic monument built from brick, timber, and glazed tiles. Yet the closer researchers examine it, the more puzzling it becomes. Hidden beneath its elegant geometry lies a collection of engineering solutions that seem remarkably advanced for the early 14th century. Even today, architects, materials scientists, and conservation specialists continue debating how builders working without modern mathematics, structural analysis software, or industrial manufacturing achieved a structure that has survived earthquakes, extreme heat, seasonal monsoons, and over 700 years of environmental stress. The monument was originally constructed between 1320 and 1324 during the rule of the Tughlaq dynasty, and later became the resting place of the famous Sufi Saint Shah Rukn-e-Alam. Archaeological investigations, architectural surveys, and modern laser measurements have revealed a building far more sophisticated than historians once assumed. What initially attracted scholarly attention was not simply its age, but its unusual combination of structural stability, geometric precision, climate control, and material durability. Each new study seemed to uncover another technical achievement that raised more questions than answers. The first mystery emerges from the monument's overall shape. Most large masonry buildings face a fundamental challenge: weight. As structures become taller, the forces pushing downward and outward increase dramatically. The builders of Shah Rukn-e-Alam addressed this problem through an octagonal design consisting of multiple progressively narrowing levels. Modern structural engineers recognize that such a configuration distributes loads more efficiently than a simple rectangular tower. The lower walls are extraordinarily thick, in some places exceeding 3 meters, creating a massive foundation capable of supporting the enormous dome above. Yet the most intriguing question is not whether the design works. The question is how medieval builders determined proportions that modern engineers would consider remarkably effective. No surviving construction manuals explain the calculations. No detailed blueprints have ever been found. The structure appears to embody sophisticated structural knowledge without leaving behind evidence of the methods used to acquire that knowledge. This puzzle becomes even more interesting when considering the region's seismic history. Southern Pakistan has experienced earthquakes throughout recorded history. Modern analysis suggests that the octagonal form helps dissipate stress more evenly than square structures, reducing the concentration of forces at corners. Similar principles appear in earthquake-resistant buildings centuries later across different parts of Asia. Whether the builders understood seismic mechanics scientifically, or developed the design through generations of observation remains unknown. Either explanation implies a level of practical engineering knowledge far greater than often attributed to the period. Inside the walls lies another technological mystery. Embedded throughout the masonry are horizontal timber bands that connect sections of brickwork. To modern engineers, this resembles a primitive form of seismic reinforcement. Timber is flexible compared with brick and can absorb movement during structural stress. Similar techniques have been documented in earthquake-resistant architecture in Kashmir, Nepal, and parts of Central Asia. However, Shah Rukn Alam presents an unusually sophisticated implementation. The timber elements were integrated into the structure from the beginning rather than added later. Even more remarkable is the fact that many of these wooden components survived for centuries while continuing to contribute to structural stability. Researchers still debate how builders selected timber species capable of resisting decay in a hot climate, and how they balance the differing expansion rates of wood and masonry without causing catastrophic cracking. Above the main chamber rises one of the monument's most impressive achievements, its dome. Studies suggest the structure employs a double shell configuration. Instead of a single massive dome, two separate layers create an internal cavity. Modern architects recognize several advantages to this approach. It reduces overall weight, improves thermal performance, and creates more visually impressive external proportions. Yet constructing a double-shell dome in the 14th century required extraordinary precision. Every brick had to be placed according to geometric relationships that maintained balance throughout construction. A slight miscalculation could have caused partial collapse before completion. Today, engineers rely on advanced calculations to model stresses in large domes. The builders of Multan achieved comparable results using methods that remain largely undocumented. The climatic performance of the tomb adds another layer to the mystery. Multan is famous for intense summer temperatures that frequently exceed 45 degrees Celsius. Under such conditions, interior spaces can become dangerously hot. Yet visitors often notice that the mausoleum remains significantly cooler than the environment outside. Researchers attribute this effect to a combination of thick walls, carefully positioned openings, thermal mass, and the insulating properties of the double dome. During the day, the masonry absorbs heat slowly, delaying temperature transfer into interior spaces. At night, accumulated heat dissipates gradually. This passive cooling system functions without electricity, machinery, or modern ventilation technology. The achievement becomes even more impressive when compared with contemporary sustainable architecture, which often attempts to recreate similar climate control principles through advanced design software. Perhaps no feature of Shah Rukn Alam inspires more fascination than its brilliant blue glazed decoration. The striking bands of turquoise and cobalt-coloured tiles remain among the most recognizable elements of the monument. Here the greatest material science mystery begins. Glazed ceramics are notoriously vulnerable to environmental degradation. Temperature fluctuations cause expansion and contraction. Moisture penetrates microscopic fractures. Salt crystallization can destroy surfaces over time. Yet significant portions of the blue glaze have survived more than 700 years. Modern laboratory analysis shows that successful ceramic glazing requires precise control over chemical composition and firing temperature. The glaze must expand and contract at rates compatible with the underlying brick. If the mismatch is too large, the surface cracks or detaches. Modern ceramic industries use sophisticated equipment to monitor such variables. Medieval craftsmen possessed none of these technologies. Nevertheless, the artisans of Multan produced glazed surfaces capable of enduring centuries of harsh environmental conditions. Scientists studying surviving tiles have identified complex interactions between silica, metallic oxides, and mineral additives. Copper compounds likely contributed to turquoise tones, while cobalt may have produced deeper blues. The challenge was not merely creating the colours. The challenge was ensuring that the glaze bonded permanently to the substrate. Even slight variations in kiln temperature could alter chemical reactions and compromise durability. Some researchers believe generations of experimentation gradually refined production techniques. Others argue that specialized knowledge networks connected craftsmen across Persia, Central Asia, and South Asia, allowing advanced ceramic technologies to spread over vast distances. What remains unexplained is the exact formula responsible for the exceptional longevity of the tiles. Despite modern analysis, no definitive reconstruction has fully replicated the long-term performance observed on the original monument. The durability of the bricks themselves presents another unresolved question. The structure has endured more than 7 centuries of environmental exposure, including intense heat, seasonal rainfall, humidity fluctuations, and biological weathering. Many younger brick monuments have deteriorated far more severely. Material studies suggest that the original bricks were manufactured under carefully controlled conditions. Their density, mineral composition, and firing characteristics appear unusually consistent. Such consistency implies a level of quality control difficult to achieve without industrial processes. Researchers continue investigating whether local clay deposits possessed unique properties or whether craftsmen employed production techniques now lost to history. Equally puzzling is the monument's geometric precision. Modern laser scans reveal remarkable symmetry across the entire structure. The octagonal plan remains balanced despite the enormous scale of construction. Vertical alignments maintain accuracy over multiple levels. The dome sits almost perfectly centered above the chamber below. Achieving such precision today is relatively straightforward, using laser instruments, total stations, and computer modeling. 14th century builders relied on ropes, plumb lines, wooden measuring tools, and geometric methods passed through apprenticeship traditions. The level of accuracy preserved in the monument suggests that medieval surveyors possessed highly refined techniques that have not been fully reconstructed by historians. The Rock of Gibraltar stands at the southern tip of the Iberian Peninsula, guarding the narrow gateway between the Atlantic Ocean and the Mediterranean Sea. For most visitors, it is simply a towering limestone mountain rising more than 426 meters above the water. For archaeologists, however, it represents something far more extraordinary. Hidden within its caves lies evidence that may force us to rethink what we know about human intelligence, technology, and survival. This is one of the last known refuges of the Neanderthals, a place where an ancient human species survived thousands of years longer than elsewhere in Europe. Yet the deeper scientists investigate Gibraltar, the more puzzling the story becomes. The mystery is no longer why the Neanderthals disappeared. The mystery is how they managed to survive here for so long, and whether they possessed technological knowledge far more advanced than traditionally believed. The modern archaeological story began in the 19th century when excavations in Gibraltar's caves produced one of the earliest Neanderthal skulls ever discovered. Long before the famous Neanderthal finds in Germany became widely known, Gibraltar had already yielded crucial evidence of an extinct human species. Over the following decades, systematic excavations in Gorham's Cave, Vanguard Cave, Ibex Cave, and several neighbouring sites uncovered thousands of stone tools, animal bones, hearths, and traces of daily life. Radiocarbon dating placed some of these occupations between approximately 40,000 and 30,000 years ago, making Gibraltar one of the strongest candidates for the final Neanderthal stronghold on Earth. At first glance, the location appears ideal. During the Ice Age, sea levels were dramatically lower than today. in some periods more than 100 meters below modern levels. The coastline extended several kilometers beyond the present shore. Instead of steep cliffs dropping directly into the sea, vast coastal plains stretched outward, creating rich ecosystems filled with game animals, marine resources, and freshwater sources. Yet, many Ice Age coastal environments around Europe offered similar opportunities. Gibraltar's uniqueness seems to involve something more than geography alone. One of the most controversial discoveries emerged from the floor of Gorham's Cave. Archaeologists uncovered a series of deeply incised lines carved into bedrock. The pattern resembles a geometric lattice formed by intersecting grooves. Laboratory analysis demonstrated that the markings were not accidental scratches caused by butchering activities or natural processes. Experimental archaeologists attempted to reproduce the engraving using stone tools and found that hundreds of deliberate strokes were required. Creating the pattern may have taken several hours of concentrated effort. This finding created a profound challenge for traditional interpretations of Neanderthal cognition. For decades, many researchers believed symbolic thinking belonged exclusively to Homo sapiens. Yet the Gorham engraving appears intentionally abstract. Unlike hunting marks or practical notches, it serves no obvious functional purpose. Similar symbolic behavior is often associated with later cave art in sites such as Lascaux or Chauvet in France. If Neanderthals created geometric symbols independently, then the intellectual gap between them and modern humans may have been far smaller than previously assumed. The mystery remains unresolved because no one knows exactly what the engraving represented. Was it art, communication, territorial marking, ritual behavior, or something entirely different? Even more intriguing is the evidence for sophisticated fire management. Throughout multiple occupation layers, archaeologists discovered repeated hearth locations positioned in remarkably consistent areas of the caves. These locations appear to maximize warmth while minimizing smoke accumulation. Modern airflow modeling suggests that certain parts of Gorham's Cave possess natural ventilation advantages. The recurring placement of hearths implies that Neanderthals may have understood these airflow dynamics through observation and experience. This may sound simple, but it represents a surprisingly advanced form of environmental engineering. Modern cave explorers often struggle with smoke buildup when using fires in enclosed spaces, yet Neanderthals repeatedly selected optimal locations over thousands of years. Comparable principles are used in traditional architecture worldwide, from Native American pit houses to Roman hypocaust systems, where airflow management significantly affects habitability. The question is whether Gibraltar's inhabitants consciously understood these principles, or whether generations of experimentation gradually produced practical engineering knowledge. However, the most fascinating mystery involves the sea itself. For much of the 20th century, Neanderthals were portrayed as specialized hunters, focused primarily on large terrestrial mammals such as deer, horses, and wild cattle. Gibraltar shattered that assumption. Excavations revealed extensive remains of marine resources, including shellfish, fish, seals, seabirds, and even dolphins. These discoveries transformed understanding of Neanderthal subsistence strategies. The implications are enormous. Harvesting marine resources consistently is not simply a matter of collecting food. It requires detailed knowledge of tidal cycles, seasonal migrations, wave conditions, weather patterns, and animal behavior. Modern coastal communities often rely upon generations of accumulated ecological knowledge to exploit marine environments efficiently. The evidence from Gibraltar suggests Neanderthals may have developed a comparable understanding tens of thousands of years earlier. Researchers found remains of monk seals and dolphins bearing cut marks associated with butchery. Some scientists propose opportunistic scavenging of stranded animals. Others argue that repeated exploitation indicates more systematic strategies. The debate remains open because direct evidence of watercraft has never been discovered. Organic materials such as wood, rope, and hide rarely survive for tens of thousands of years. Consequently, the archaeological record preserves only fragments of the story. The possibility of advanced coastal resource management becomes even more compelling when Gibraltar is compared with other prehistoric sites. At South Africa's Pinnacle Point, early Homo sapiens exploited shellfish approximately 160,000 years ago. At Portugal's Figueira Brava, Neanderthals also consumed substantial quantities of marine food. Gibraltar belongs to a growing collection of sites suggesting that coastal adaptation was not unique to modern humans. Instead, Neanderthals may have independently developed sophisticated maritime survival strategies. Yet a fundamental mystery remains unanswered. How did they acquire and transmit this knowledge? Modern societies preserve technical expertise through writing, schools, and digital archives. Neanderthals possessed none of these systems. Nevertheless, the archaeological evidence indicates continuity across many generations. Successful exploitation of marine environments requires accumulated experience. Mistakes can be fatal. Dangerous tides, storms, and unpredictable currents punish ignorance quickly. The persistence of coastal resource use suggests some mechanism for preserving knowledge over long periods. This invisible technology of knowledge transmission may represent one of the greatest lost achievements of the Neanderthal world. Another mystery concerns navigation. Gibraltar occupies one of the most strategically important locations on Earth. The Strait of Gibraltar narrows to approximately 14 kilometers at its closest point, creating a natural bottleneck between two continents. During the Ice Age, the surrounding landscape offered extensive views across both land and sea. Archaeological evidence indicates repeated occupation of the region over thousands of years. Groups continued returning to the same caves despite climatic fluctuations and environmental changes. Such consistency suggests detailed mental mapping of the landscape. Anthropologists often describe this as cognitive geography, the ability to store and transmit spatial knowledge without written maps. Modern hunter-gatherer societies sometimes maintain astonishingly precise mental representations of territories spanning hundreds of kilometers. Whether Neanderthals possessed comparable capabilities remains uncertain, but Gibraltar provides some of the strongest evidence supporting that possibility. What do you think? Were the Neanderthals of Gibraltar simply skilled survivors, or were they possessors of a lost body of knowledge that modern science still underestimates? Share your thoughts in the comments below. Near the modern border of Turkmenistan and Iran, in a dry landscape where wind, drought, invasion, and time have erased countless ancient settlements, the ruins of Abiverd still preserve traces of a city that endured for centuries. Archaeologists have uncovered walls, fortifications, irrigation systems, and urban structures that reveal a level of engineering far beyond what the environment would seem to allow. Yet the deeper researchers investigate the site, the more difficult it becomes to explain how a city built largely from earth and mud resisted destruction for so long. The ruins remain, but much of the knowledge that created them has vanished. The ruins of Abiverd have been known locally for centuries, but systematic archaeological investigations expanded during the 20th century as Soviet and Central Asian researchers began documenting ancient settlements across southern Turkmenistan. Excavations revealed that Abiverd occupied a strategic position along major trade corridors connecting Persia, Central Asia, and the eastern regions of the Silk Road. Beneath layers of collapse, archaeologists discovered evidence of multiple construction phases spanning many centuries, indicating that the city was repeatedly rebuilt, expanded, and maintained by successive generations. At first glance, Abu Verd appears similar to many forgotten cities of Central Asia. The region experiences harsh seasonal temperature variations, with summer temperatures frequently exceeding 40 degrees Celsius, while winter conditions can become severe. Annual rainfall remains relatively low, compared with the agricultural heartlands of Mesopotamia or the Nile Valley. Yet archaeological surveys suggest that Abu Verd once supported a substantial urban population, and this immediately presents a puzzle. Cities require reliable water, food production, transportation networks, defensive infrastructure, and long-term maintenance. Every one of these systems depends upon stable environmental management. Modern hydrological models indicate that sustaining large populations in semi-arid environments demands careful control of water resources, and even minor disruptions can trigger agricultural decline. The fact that Abu Verd persisted for centuries suggests that its inhabitants possess sophisticated environmental knowledge that is only partially visible in the surviving archaeological record. Traces of canals, reservoirs, and agricultural systems indicate deliberate water management. However, the complete network no longer exists. Erosion, later settlement, and natural landscape changes have erased large portions of the original infrastructure. As a result, researchers can identify fragments of the system but cannot fully reconstruct how the entire hydraulic network functioned. This missing information creates one of the site's most enduring mysteries. The city clearly had access to enough water to survive. The question is how? The greatest engineering mystery of Abu Verd is not its walls, it is the fact that those walls still exist at all. Much of the city was constructed using earthen materials including mud brick, rammed earth, and locally available sediments. According to conventional expectations, such structures should be extremely vulnerable to erosion. Water infiltration weakens mud brick, wind abrasion gradually removes exposed surfaces, and repeated temperature fluctuations produce cracking and structural degradation. Yet portions of Abu Verd remained standing for centuries. Some sections survived invasions, others endured earthquakes, storms, and abandonment, and even after the city declined, significant portions of its architecture resisted complete destruction. The question is why? Modern material scientists studying ancient earthen architecture have discovered that durability depends heavily on factors such as particle distribution, clay content, moisture regulation, compaction techniques, and organic additives. Small variations in composition can dramatically alter structural performance. Experiments conducted on traditional mud brick structures in Central Asia have shown that carefully optimized mixtures can achieve compressive strengths several times greater than poorly prepared equivalents. Certain natural fibers can reduce crack propagation, specific clay-to-sand ratios improve stability, and multi-layer wall systems can enhance moisture resistance. The challenge is that archaeologists cannot yet determine every variable used by the builders of Abu Verd. The surviving walls function almost like fragments of a lost engineering manual. Researchers can measure the results, but they cannot completely reconstruct the process. This situation mirrors mysteries found elsewhere across the ancient world. The massive earthen citadel of Bam in Iran survived for nearly 2,000 years before the devastating earthquake of 2003. Sections of the Great Wall of China constructed from rammed earth remained stable for centuries in harsh desert environments. Ancient settlements across Central Asia repeatedly demonstrated that earthen architecture could perform far beyond modern expectations. Abu Verd belongs to this tradition. Its builders appear to have understood material behavior at a remarkably advanced level despite possessing none of the analytical tools available today. The deeper mystery is whether this knowledge was gained through centuries of experimentation, transmitted through specialized craftsmen, or preserved through engineering traditions that disappeared with the city itself. The ruins also reveal evidence of deliberate planning. Archaeological mapping indicates organized defensive lines, structured urban zones, and carefully positioned construction. Such arrangements may seem ordinary today, but ancient surveyors lacked laser levels, satellite imagery, total stations, and computer-generated maps. Everything depended upon observation, measurement, and geometry performed directly on the landscape. Across the ancient world, civilizations repeatedly achieved astonishing accuracy using surprisingly simple tools. Egyptian builders aligned the Great Pyramid to true north with an error of only a few arc minutes. Roman engineers constructed aqueducts with gradients measured in centimeters per kilometer. Ancient Persian builders designed qanat systems that transported groundwater across vast distances using extremely precise slopes. Abu Verd appears to reflect the same tradition of practical engineering intelligence. The layout suggests planning that extended beyond individual structures. Someone understood how the city should function as a complete system. The challenge for modern archaeology is determining exactly how such measurements were achieved and maintained across generations. No technical manuals survive, no engineering diagrams remain, and only the physical results continue to speak. Water remains one of the site's greatest unanswered questions. Every major civilization depended upon hydraulic engineering. Mesopotamia relied on canals. Egypt depended on Nile flood management. Persia mastered underground qanat systems, and the cities of Central Asia often combined multiple techniques. Abu Verd almost certainly required a comparable solution. Remote sensing surveys and archaeological investigations have identified traces of ancient channels and agricultural zones surrounding the settlement. These features suggest a coordinated system rather than isolated projects. However, large portions of the network have disappeared. Rivers change course, canals become buried, reservoirs fill with sediment, and thousands of years of environmental change can erase critical evidence. Some researchers argue that the surviving remains represent only a small fraction of the original infrastructure. If true, the engineering capabilities of Abu Verd may have been significantly greater than current evidence suggests. The mystery is not whether the system existed. The mystery is how extensive it once was. The city's defensive structures create another engineering puzzle. Ancient walls are often admired for their appearance, but their construction required enormous logistical effort. Even earthen fortifications demand massive quantities of material. Workers must excavate soil, transport it, compact it, shape it, reinforce it, and maintain it over time. Calculations from comparable ancient fortifications indicate that large defensive earthworks can involve hundreds of thousands of cubic meters of material movement. Without mechanized equipment, every stage depends upon human labor. This raises difficult questions about how many workers participated, how labor was organized, who coordinated construction, and how resources were supplied. The physical remains demonstrate that such systems existed, but the administrative mechanisms behind them remain largely invisible. Like many ancient cities, Abu Verd preserves the product while concealing the process. Castle of Oria stands on a fractured limestone hill in Apulia, southern Italy. For nearly 1,000 years, earthquakes, erosion, warfare, and gravity should have torn it apart. Instead, the fortress remains anchored to a hill that geologists describe as one of the most difficult foundations on which a major defensive structure could be built. The real mystery is not why the castle was constructed. The mystery is how medieval engineers managed to build a massive stone fortress on unstable karst rock, with a level of structural stability that still challenges explanation today. The castle was never truly discovered because it has dominated the skyline of Oria for centuries. However, systematic archaeological and architectural studies conducted during restoration projects revealed something unexpected. Beneath a visible medieval structure lies evidence of continuous occupation stretching back through Norman, Byzantine, Lombard, Roman, and possibly even Messapian periods. Each generation modified the fortress, but the most remarkable feature remained unchanged: its relationship with the hill itself. Researchers initially focused on military history, but over time engineers became increasingly interested in the site's geology, drainage systems, foundation placement, and unusual defensive geometry. The deeper they investigated, the more difficult it became to explain how builders working without modern surveying instruments achieved such long-term structural success. The greatest engineering mystery of Castle of Oria lies beneath its walls. The fortress stands on a hill composed largely of limestone affected by karst processes. Karst terrain forms when groundwater slowly dissolves rock over thousands or millions of years, creating fractures, cavities, sinkholes, and underground voids. Modern civil engineers often consider karst landscapes among the most dangerous environments for large construction projects. Today, major buildings constructed on karst foundations typically require extensive geological surveys, drilling programs, ground-penetrating radar, and computer modeling before construction begins. Even with these technologies, unexpected collapses still occur. Yet the builders of Oria somehow succeeded centuries before any of these tools existed. Geological studies show that the hill contains numerous natural discontinuities and fractures. Such weaknesses normally create differential settlement, meaning one part of a structure sinks faster than another. Differential settlement is responsible for many historic structural failures worldwide. The question becomes obvious. How did medieval builders know where to place thousands of tons of stone? The castle's walls appear to rest precisely on the most stable portions of the hill. Critical load-bearing sections correspond remarkably well with areas of stronger bedrock, while less critical structures occupy zones where the geology is less reliable. This placement could be coincidence, but many engineers doubt coincidence alone can explain such consistent success. One possibility is that builders inherited empirical geological knowledge accumulated over centuries. They may have observed how natural cracks behaved after heavy rainfall, how rock surfaces fractured under impact, and which locations resisted movement during earthquakes. If true, they possessed a practical understanding of foundation engineering that existed entirely outside written science. The knowledge vanished, but the evidence may still be embedded within the castle itself. At first glance, Castle of Oria appears irregular. Unlike many idealized medieval fortresses designed around symmetry, Oria's towers and walls follow an asymmetric layout. For generations, historians viewed this as a consequence of adapting construction to the hill's shape. Modern military analysis suggests something more sophisticated. The fortress features a triangular defensive arrangement reinforced by massive towers positioned at key observation points. Computer visibility studies demonstrate that these positions minimize blind spots while maximizing overlapping fields of observation. In practical terms, defenders could monitor nearly every approach route. What makes this remarkable is the absence of modern surveying equipment. Theodolites would not appear for centuries. Laser rangefinders were unimaginable, and digital terrain models did not exist. Yet the castle's geometry achieves many of the same defensive outcomes produced by modern military planning software. Some researchers believe medieval engineers relied on advanced practical geometry developed through generations of fortress construction, while others argue that repeated rebuilding gradually refined the design. Neither explanation fully accounts for the extraordinary effectiveness of the final arrangement. Every fortress faces the same challenge. An army can survive attacks, but it cannot survive without water. Castle of Aurea occupies a hilltop lacking major natural springs, meaning that during sieges, water supply would determine whether defenders lived or died. To solve this problem, builders created an intricate rainwater collection system. Channels carved into stone directed runoff toward underground cisterns, while storage chambers were strategically positioned throughout the fortress. Carefully calculated gradients allowed water to flow efficiently while minimizing erosion and contamination. The mystery lies in the precision. Hydraulic systems are unforgiving. A slope that is too steep accelerates erosion, while a slope that is too shallow causes stagnation. Even small errors can render an entire collection network ineffective. Yet many components functioned successfully for centuries. When engineers compare medieval water systems across Europe, the sophistication of Aurea's drainage network places it among a select group of fortifications demonstrating unusually advanced hydraulic planning. The builders left no equations, the water itself became the proof. Southern Italy has experienced significant seismic activity throughout history. Many medieval structures collapsed, but Castle of Aurea survived, not perfectly, but remarkably well. Its survival raises questions about ancient understanding of structural behavior. The walls are exceptionally thick, mass is distributed unevenly across the fortress, and load-bearing sections follow natural contours of the hill, rather than imposing rigid geometric patterns upon it. Modern earthquake engineering often emphasizes flexibility and energy dissipation. Medieval builders obviously lacked the mathematical tools required to calculate seismic forces. Nevertheless, some of their solutions produced comparable outcomes. Rather than fighting the landscape, the fortress adapts to it. Instead of forcing perfect symmetry, the design accepts irregularity. Paradoxically, this may have increased resilience. The same principle appears in other long-lasting structures, including sections of the Inca citadel of Machu Picchu and parts of ancient Japanese castle architecture, where adaptation to terrain often proved more durable than geometric perfection. Whether this was intentional engineering or accumulated experience remains uncertain. Subterranean spaces beneath the castle add another layer of intrigue. Researchers have identified underground chambers, storage areas, and passageways integrated into the hill itself. Some may have served military purposes, while others likely functioned as storage facilities. What attracts scientific attention is their thermal stability. Even during periods of extreme Mediterranean heat, temperatures underground remain relatively constant. Modern architects intentionally design passive cooling systems based on the same principle. Ancient builders obviously lacked thermodynamic equations, yet many historical structures demonstrate surprisingly effective climate control. Whether the builders understood the physics or merely mastered it through observation remains one of the site's unanswered questions. What do you think was the real secret behind Castle of Aurea's survival? Lost engineering knowledge, centuries of trial and error, or something we still haven't fully understood? Share your thoughts in the comments below. Shikarpur is a forgotten city buried in the Kutch region of Gujarat, Western India. At first glance, it appears to be just another settlement of the Indus Valley civilization. But beneath layers of earth lies a mystery that challenges conventional assumptions about Bronze Age technology. Archaeologists uncovered evidence suggesting that more than 4,000 years ago, Shikarpur may have operated as something remarkably close to an industrial production centre, a place where thousands of objects were manufactured with a level of consistency, precision and quality control that remains difficult to explain. The site was identified through archaeological surveys in the late 20th century and later excavated by researchers investigating Harappan settlements across Gujarat. What emerged from the excavations was not merely a residential town, but a landscape filled with workshops, production debris, stone beads, pottery, metal objects, and evidence of specialized manufacturing. The discoveries raised a question that continues to puzzle archaeologists today. How did a Bronze Age society lacking iron tools, advanced machinery, or written technical manuals achieve such extraordinary levels of standardization? The greatest mystery of Shikarpur begins with mass production. Modern manufacturing depends on measurement systems, quality control procedures, training manuals, and specialized tools. Factories producing millions of identical objects rely on machines capable of repeating precise actions. Yet thousands of years before industrialization, the people of Shikarpur appear to have solved many of the same problems. Excavations revealed large numbers of beads made from carnelian, agate, chalcedony, and faience. Many of these objects display dimensions that vary only slightly from one specimen to another. Statistical studies conducted on Harappan weights across the Indus civilization have demonstrated remarkable standardization, often based on binary and decimal progressions. Similar patterns appear in manufactured objects found at sites such as Harappa, Mohenjo-daro, Dholavira, Lothal, and Shikarpur. The implications are extraordinary. To produce thousands of nearly identical beads, craftsmen would have required a system capable of controlling raw materials, shaping procedures, drilling techniques, polishing methods, and final inspection standards. Every stage would have needed consistency, and a single poorly drilled bead could ruin the entire product. Today, such consistency would be expected from precision manufacturing equipment. In the Bronze Age, however, the mechanism behind this standardization remains largely invisible. No instruction manuals survive, no workshop regulations have been found, and most importantly, the Indus script remains undeciphered. This means researchers can see the results of the production system but cannot fully understand the organizational structure that created it. It is similar to discovering a modern factory after all its documents have been destroyed. The products remain, but the process has vanished. The mystery deepens when examining the drilling technology. Many stone beads discovered throughout the Indus civilization contain incredibly narrow perforations, running through extremely hard materials. Some beads from Harappan contexts required drilling channels several times longer than their diameter. Experimental archaeologists attempting to recreate these artifacts have demonstrated that the process is surprisingly difficult, even with modern reproductions of ancient tools. Carnelian measures approximately 6.5 to 7 on the Mohs hardness scale, and agate possesses similar hardness. Drilling through such materials requires abrasive compounds harder than the stone itself. Archaeological evidence suggests Harappan craftsmen may have used specialized drill bits, combined with quartz, sand, corundum, or other abrasive materials. Yet this explanation only partially solves the puzzle. Precision is not the same as possibility. Modern experiments show that producing one successful bead is achievable, but producing thousands with consistent dimensions over centuries is an entirely different challenge. The drill holes often remain remarkably straight, deviations are minimal, and failures appear relatively uncommon compared to the volume of successful products. The question is not whether the technology worked. The question is how the technology was maintained and transmitted across generations. Knowledge preservation presents another unsolved mystery. Most civilizations leave behind technical texts. Ancient Egypt recorded construction methods, Mesopotamia preserved administrative records, and classical civilizations documented engineering principles. At Shikarpur, the technical knowledge itself remains hidden behind an undeciphered writing system. The craftsmen clearly understood geology, mineral properties, heat treatment, drilling mechanics, and polishing techniques. They possessed practical expertise accumulated over centuries, yet the mechanism through which this knowledge survived remains unknown. Perhaps apprentices learned directly from masters. Perhaps specialized guilds controlled production. Perhaps the Indus script contains technical information that scholars simply cannot read. Until the script is deciphered, the intellectual infrastructure behind Harappan manufacturing remains one of archaeology's greatest blind spots. Another technological puzzle emerges from the evidence of long-distance trade. Shikarpur occupied a strategic position near routes connecting inland settlements with coastal regions of the Arabian Sea. Chemical analyses of artifacts found throughout the Indus world indicate that raw materials often travelled hundreds of kilometres before reaching workshops. Carnelian originated from specific geological sources. Copper came from mining regions located far from manufacturing centres, and marine shells arrived from coastal environments. Finished products then circulated across vast networks, extending from western India to regions connected with ancient Mesopotamia. Some scholars estimate that Indus trade networks covered more than 1 million square kilometres. For comparison, this territory exceeded the size of many later Bronze Age states. The logistical challenge is staggering. Modern supply chains require communication systems, inventories, transportation planning, and quality monitoring. Yet Shikarpur functioned within a civilization that left no deciphered records explaining how these operations were coordinated. The products suggest organization, the archaeology suggests complexity, but the documentation is silent. Evidence of metallurgy introduces another layer of mystery. Excavations at Shikarpur recovered metal artifacts alongside traces of manufacturing activity. Bronze Age metallurgy demanded precise temperature control. Copper melts at approximately 1085 degrees Celsius. Producing reliable metal tools required not only high temperatures, but also control over airflow, fuel quality, furnace design, and cooling procedures. Ancient metallurgists possessed no thermometers and had no scientific understanding of atomic structure, yet they repeatedly achieved results that modern analysis confirms were technically sophisticated. Archaeometallurgical studies across Harappan sites indicate knowledge of alloying techniques and controlled production methods. The challenge for researchers is that furnaces rarely survive intact. What remains are fragments, slag deposits, and finished products. Once again, the results are visible while the process remains partly hidden. Perhaps the most overlooked mystery involves environmental engineering. The Kutch region is not an easy place to inhabit. It experiences periods of drought, fluctuating water availability, seasonal extremes, and changing environmental conditions. Maintaining a permanent settlement under such circumstances required careful resource management. Shikarpur survived within this landscape for centuries. Its inhabitants had to secure water supplies, support manufacturing activities, sustain trade networks, and feed a growing population. Such stability suggests a deep understanding of local geography and climate. Recent studies of Harappan settlements indicate that many communities adapted strategically to changing environmental conditions rather than collapsing suddenly. If true, Shikarpur may represent evidence of sophisticated environmental planning long before modern concepts of sustainability emerged. Qatar's ancient ruins are scattered across one of the harshest environments on Earth. Today, the peninsula receives less than 100 millimeters of rainfall annually. Summer temperatures regularly exceed 45 degrees Celsius, and fresh water remains one of the region's most valuable resources. Yet archaeologists investigating sites such as Al-Zubara, Murwab, Kalat Murair, and Al-Jassasiyah have uncovered evidence that thriving communities once flourished here for centuries. The discovery emerged through a combination of archaeological surveys, satellite mapping, and excavations conducted throughout the 20th and 21st centuries. What initially appeared to be ordinary desert settlements soon revealed a series of engineering puzzles that remain difficult to explain. The deeper researchers examine ancient Qatar, the less the question becomes who lived here. The real question is how they repeatedly solved technical problems that would challenge even modern engineers working in the same environment. One of the greatest mysteries involves water. Every permanent settlement depends on reliable access to fresh water, yet Qatar possesses no major rivers and very limited natural freshwater reserves. Modern hydrogeological studies show that groundwater in many parts of the peninsula exists only in fragile underground aquifers vulnerable to depletion and saltwater intrusion. Nevertheless, archaeological excavations have revealed networks of wells, storage facilities, and water management systems capable of supporting surprisingly large populations. At Al Zubarah alone, the urban area covered roughly 60 hectares during its peak, sustaining thousands of residents, merchants, craftsmen, and sailors required continuous water supplies in an environment where annual evaporation rates exceed rainfall many times over. The mystery is not simply that wells existed, it is how ancient builders repeatedly located productive groundwater sources with remarkable accuracy. Modern drilling projects rely on geological surveys, hydrological mapping, and increasingly sophisticated remote sensing technologies. Ancient Qatar possessed none of these tools, yet settlement after settlement appears strategically positioned near the most reliable freshwater resources available. Researchers suspect that generations of accumulated environmental knowledge allowed inhabitants to recognize subtle geological indicators invisible to outsiders. Even so, the exact methods remain unknown. The water systems themselves survived. The knowledge that guided their placement largely vanished. Construction technology presents another puzzle. Many structures across ancient Qatar were built using coral stone, limestone, gypsum mortar, and imported timber. On paper, these materials should have been highly vulnerable to the peninsula's extreme climate. Salt-laden coastal winds accelerate deterioration. Daily thermal expansion and contraction create structural stress. Wind-driven sand acts like natural sandpaper, gradually eroding exposed surfaces. Yet numerous walls, fortifications, foundations, and towers survived for centuries. Material scientists studying historic Gulf architecture have discovered that traditional gypsum mortars often exhibit properties that seem surprisingly optimized for desert environments. Some mixtures remain flexible enough to absorb thermal stress while maintaining sufficient strength for structural stability. In certain samples, microscopic analysis reveals carefully controlled particle distributions and mineral compositions. The builders obviously lacked modern chemistry, yet they consistently produced materials capable of surviving conditions that destroy many contemporary structures. The question is whether this knowledge resulted from centuries of experimentation or whether more systematic technical traditions once existed but were never recorded. The ruined city of Al Zubarah introduces an even more sophisticated challenge. Unlike many settlements that evolved organically over time, large portions of the city display evidence of deliberate planning. Streets intersect at predictable angles. Residential districts, defensive zones, commercial areas, and harbour facilities appear organised according to coherent principles. Ground-penetrating surveys have revealed urban layouts extending beyond visible ruins, suggesting a level of planning that exceeds simple incremental growth. Urban planning on this scale requires more than construction skills, it requires surveying. Modern surveyors use theodolites, GPS systems, laser measurements, and mathematical coordinate systems. ancient builders possessed none of these technologies. Nevertheless, numerous archaeological sites throughout the ancient world demonstrate surprisingly accurate alignment and spatial organization. Al-Zubarah joins a list that includes Roman military camps, Indus Valley cities such as Mohenjo-Daro, and parts of ancient Egyptian settlements where geometric consistency appears far greater than chance alone would predict. How surveyors in Qatar achieved this precision remains uncertain. The peninsula's defensive architecture raises similar questions. Kalat Merer and other fortified locations occupy positions that maximize visibility while protecting access to critical resources. Their placement reflects a sophisticated understanding of terrain, movement corridors, and strategic observation. Modern military planners would analyze such positions using topographic models, satellite imagery, and geographic information systems. Ancient builders relied entirely on direct observation. Yet many of their decisions appear remarkably effective when evaluated through modern and analytical methods. Even more mysterious are the petroglyphs of Al-Jassasiyah. More than 900 carvings are scattered across limestone outcrops in northeastern Qatar. Some depict boats. Others consist of geometric arrangements of cup-shaped depressions carved into rock surfaces. The carvings have attracted decades of study, but no explanation fully accounts for their purpose. Certain researchers propose that the cup marks may have served as gaming boards. Others suggest ritual functions. More speculative theories connect them to navigation, astronomy, or resource management. What keeps the mystery alive is the extraordinary diversity of patterns. Some arrangements appear random, others display striking symmetry. A few resemble organized information systems rather than decorative art. The maritime carvings deepen the puzzle. Qatar's economy depended heavily on seafaring, fishing, and pearl diving for centuries. Long before modern navigation, sailors crossed the Persian Gulf and connected trade networks stretching toward Mesopotamia, Persia, India, and East Africa. Navigating these routes required intimate knowledge of currents, winds, coastlines, stars, and seasonal weather patterns. Yet archaeologists have recovered remarkably little direct evidence explaining how this knowledge was stored and transmitted. No extensive maritime manuals survive. No sophisticated navigational instruments comparable to later astrolabes have been discovered. Nevertheless, sailors repeatedly crossed dangerous waters with impressive reliability. Comparisons with Polynesian navigation reveal an intriguing possibility. Polynesian voyagers traversed thousands of kilometers of open ocean using mental maps, wave patterns, celestial observations, and oral traditions. Ancient Gulf navigators may have employed similarly advanced cognitive systems. If so, much of their technological expertise existed not in physical objects but in human memory. Trade networks provide another layer of complexity. Archaeological evidence demonstrates that Qatar participated in commercial systems spanning enormous distances. Imported ceramics, metals, timber, and luxury goods reached the peninsula from regions hundreds or even thousands of kilometers away. Maintaining such connections required logistical coordination comparable to that found in much larger civilizations. Consider the challenge quantitatively. A single merchant vessel crossing the Gulf had to account for weather variability, water supplies, cargo preservation, navigation, and harbor access. Multiply this process across generations and trade routes extending from Mesopotamia to the Indian Ocean, and an invisible infrastructure of knowledge emerges. Trade was not merely the movement of goods, it was the movement of information. Construction techniques, resource management strategies, navigational methods, and material technologies likely spread through these networks. Yet tracing these pathways remains extraordinarily difficult. Skala Podilska is perched above the Zbruch River in western Ukraine, where archaeologists investigating a ruined fortress discovered something unexpected. The castle itself was not unusual. Europe is filled with medieval fortifications. What puzzled researchers was its location. The fortress stands on a steep rocky outcrop overlooking a deep river valley, a position that should have created enormous engineering difficulties centuries before modern surveying equipment, structural analysis, or mechanized construction. Yet parts of the fortification survived wars, earthquakes, weathering, and centuries of neglect. The deeper historians, archaeologists, and engineers examine the site, the more difficult it became to explain how builders working with limited technology repeatedly solved problems that remain challenging even today. The earliest fortifications in the region likely appeared during the medieval period, although the strategic importance of the location may extend much further back. Historical records suggest that various powers occupied and rebuilt the fortress over centuries as control of the frontier shifted between competing kingdoms and empires. Every reconstruction added another layer to the mystery. Rather than abandoning the difficult terrain, successive builders repeatedly chose to invest labor, materials, and resources into strengthening a site that presented extraordinary logistical challenges. The first puzzle emerges from the landscape itself. The fortress occupies a limestone promontory rising sharply above the surrounding valley. Modern engineers understand that construction on elevated rocky terrain introduces numerous risks. Access routes become difficult. Material transport becomes expensive. Foundations must be carefully adapted to uneven geological conditions. Every ton of stone moved uphill requires significant labor. Yet medieval builders selected one of the most difficult locations imaginable and then proceeded to erect massive defensive walls. The scale of this challenge becomes clearer when compared with other famous hilltop fortresses. Sites such as Masada in Israel, Sigiriya in Sri Lanka, and the castles of southern Italy all required enormous organizational effort to transport construction materials to elevated positions. Experimental archaeology suggests that moving a single large stone block uphill without machinery may require dozens of workers. When multiplied across thousands of blocks, the total labor investment becomes staggering. Skala Podilska raises the same question found at many ancient and medieval strongholds. How did builders coordinate the movement of such quantities of material with remarkable efficiency, despite possessing no engines, cranes, or powered lifting systems? The geology introduces an even deeper mystery. Limestone formations often contain fractures, cavities, and hidden weaknesses produced by water erosion over thousands of years. Modern geotechnical engineers routinely conduct extensive surveys before constructing heavy structures on such terrain. Ground-penetrating radar, core sampling, and computer modeling are standard procedures. Medieval builders possessed none of these tools. Nevertheless, large sections of Skala Podilska remained structurally stable for centuries. Researchers studying historical construction frequently encounter evidence suggesting that ancient builders possessed sophisticated practical knowledge of geology. They may not have understood rock mechanics in mathematical terms, but they appear to have recognized subtle indicators of stability through observation and experience. At Skala Podilska, builders somehow identified portions of the rocky plateau capable of supporting substantial defensive structures while avoiding catastrophic foundation failures. Exactly how they accomplished this remains poorly understood because the knowledge was transmitted through generations of craftsmen rather than formal engineering manuals. The fortress also reveals intriguing evidence of adaptation to technological change. During the late medieval period, gunpowder transformed warfare throughout Europe. Traditional high walls designed to repel ladders and siege towers suddenly became vulnerable to artillery bombardment. Many castles quickly became obsolete. Others underwent extensive modifications. At Skala Podilska, surviving remains indicate that defensive structures were strengthened and redesigned to accommodate the new reality of cannon warfare. This adaptation presents an engineering puzzle. Modern structural analysis allows engineers to calculate how walls respond to impact forces. Medieval builders lacked such equations, yet they frequently developed remarkably effective solutions. Thicker walls, modified bastions, and altered defensive angles appear throughout European fortifications from this gunpowder era. Skala Podilska demonstrates this same pattern. Builders seem to have understood through experience how geometry could dissipate destructive energy. The result was a fortress capable of surviving military technologies that had rendered countless older strongholds ineffective. Another mystery concerns the geometry of defense. Archaeological surveys indicate that many surviving wall segments and towers were positioned to maximize visibility across approaches to the fortress. Modern military planners refer to overlapping fields of fire, where multiple defensive positions can target the same area simultaneously. Such arrangements eliminate blind spots and increase defensive effectiveness. Achieving this level of optimization without aerial photography, satellite imagery, or advanced surveying equipment required extraordinary spatial awareness. Builders needed to evaluate lines of sight across rugged terrain, estimate distances, and account for natural obstacles. Similar geometric sophistication appears at famous sites ranging from Roman frontier forts to Crusader castles. Skala Podilska demonstrates that medieval engineers often possessed practical surveying skills far more advanced than popular imagination suggests. Water management may represent the greatest unanswered question. Every fortress faces the same fundamental problem. During a siege, defenders cannot rely upon external water sources. A stronghold without a secure water supply becomes vulnerable regardless of the strength of its walls. Historical fortifications around the world developed ingenious solutions. Masada stored enormous quantities of rainwater in giant cisterns. Crusader castles constructed elaborate collection systems. Byzantine fortresses incorporated hidden reservoirs. The exact water infrastructure of Skala Podilska remains incompletely understood because much of it has disappeared. Yet the fortress could not have functioned effectively without a reliable system for collecting, storing, and distributing water. Archaeologists suspect that now-lost cisterns, underground chambers, and drainage networks once played a critical role in sustaining the population during periods of isolation. The challenge is reconstructing systems that no longer survive in complete form. Every missing stone removes another piece of the engineering puzzle. The materials themselves create another mystery. The climate of western Ukraine subjects masonry to repeated freeze-thaw cycles. Water penetrates cracks, freezes, expands by approximately 9%, and gradually fractures stone and mortar. Over centuries, this process can destroy even robust structures. Yet portions of Skala Podilska survived far longer than many comparable fortifications. Conservation scientists studying historical masonry frequently discover that ancient builders employed mortar formulas far more sophisticated than previously assumed. Some mixtures incorporated crushed brick, reactive minerals, lime compounds, or organic additives that enhance durability. Similar discoveries have transformed understanding of Roman concrete, which continues to attract scientific attention because of its remarkable longevity. The precise composition of construction materials used at Skala Podilska remains only partially understood. Researchers continue investigating whether local builders possess specialized knowledge of mortar preparation that improved resistance to weathering. If such techniques existed, much of that expertise vanished alongside the craftsmen who developed it. Surkania was discovered among the limestone uplands of northwestern Syria, part of the region archaeologists call the Dead Cities. At first glance, it appears to be little more than another abandoned Byzantine village scattered across rocky hills. Yet the moment researchers began documenting its churches, houses, stone-built inns and agricultural infrastructure, a disturbing question emerged. How did the relatively small rural community develop construction techniques capable of surviving nearly 15 centuries in one of the most politically unstable and seismically active regions of the Middle East? The ruins themselves remain silent, but every wall, arch, and carved stone suggests the existence of engineering knowledge that historians still struggle to fully explain. The first surveys revealed something unexpected. Unlike many ancient settlements whose monuments depended heavily on mortar, Surkania relied largely on precisely cut limestone blocks. The region's buildings were not protected by modern restoration for most of their existence. They endured centuries of earthquakes, warfare, neglect, weathering, and structural stress. Yet many walls remain standing. Some doorways preserve their original geometry. Portions of churches built during the 4th through 6th centuries still display remarkable stability. Engineers examining similar structures throughout Syria's dead cities have noted that their survival rates often exceed what might be expected from buildings of comparable age elsewhere in the Mediterranean. The mystery begins with the stone itself. Limestone is abundant across northern Syria, but not all limestone behaves the same way. Some varieties fracture easily under stress. Others contain hidden weaknesses caused by bedding planes and microcracks. Ancient builders had no geological surveys, no petrographic microscopes, and no structural analysis software. Yet the stone selected for major structures appears remarkably consistent in quality. Modern material scientists can identify suitable quarry layers through laboratory testing, but Surkania's builders somehow accomplish similar results through observation and experience alone. Archaeologists still debate how quarry workers recognized which stone beds would remain stable for centuries after extraction. The buildings themselves introduce even greater puzzles. Many structures incorporated large stone lintels spanning doorways and windows. This may sound ordinary today, but stone performs exceptionally well under compression while remaining vulnerable under tension. A poorly selected lintel can crack and fail under its own weight. Nevertheless, numerous examples throughout the Dead Cities survived for more than 1,400 years. Some spans remain remarkably straight despite centuries of loading. The builders clearly understood practical limits that modern engineers would express through stress calculations, yet they possessed neither algebraic formulas nor formal structural engineering theory. Their knowledge existed entirely within a tradition that disappeared long ago. The churches of Surkania add another layer of complexity. Byzantine architecture is often associated with monumental urban centres such as Constantinople, yet even remote settlements like Surkania display sophisticated planning. Survey measurements reveal consistent geometric relationships between naves, aisles, entrances, and apses. Orientation frequently follows an east-west alignment with surprisingly small deviations. Achieving such accuracy required methods of surveying that remain poorly documented. Today, a surveyor can establish precise bearings using GPS receivers, total stations, and satellite imagery. Ancient builders relied only on simple instruments, direct observation, and astronomical references. Yet the resulting alignments often rival those achieved by much later construction traditions. One of the most overlooked mysteries involves environmental engineering. Northern Syria occupies a transitional climatic zone. Annual rainfall varies considerably from year to year, and prolonged droughts periodically affect agricultural productivity. Maintaining a permanent settlement required more than durable architecture. It required reliable water management. Archaeological evidence indicates that communities throughout the limestone massif depended upon cisterns, reservoirs, drainage systems, and rainwater collection networks. The problem is that much of this infrastructure has vanished. What remains are fragments, channels carved into bedrock, partially collapsed storage basins, and isolated hydraulic features disconnected from their original systems. Modern hydrologists studying semi-arid environments emphasize that long-term water security depends upon careful balancing of storage capacity, evaporation rates, runoff capture, and seasonal demand. Even small errors can destabilize an agricultural economy. Yet Surkania participated in a regional network supporting thousands of inhabitants across hundreds of settlements. Olive cultivation flourished, vineyards expanded, trade continued for centuries. Such stability implies sophisticated environmental management. The troubling reality is that archaeologists still cannot reconstruct the complete hydraulic systems that made this possible. Agriculture itself introduces another technological puzzle. The dead cities experienced a remarkable prosperity between the 4th and 6th centuries. Evidence suggests large-scale olive oil production throughout the region. Stone presses discovered across northern Syria demonstrate extensive processing capabilities. Producing olive oil at commercial scale requires much more than growing trees. Farmers must understand soil conditions, pruning cycles, harvesting schedules, storage techniques, and mechanical extraction processes. Modern agricultural science can quantify these variables precisely. Surkania's inhabitants possessed no such formal knowledge, yet they sustained production levels capable of supporting both local populations and regional trade networks. The settlement's architecture also hints at a surprising degree of standardization. Researchers have identified recurring design patterns across multiple villages within the dead cities. Doorways often follow similar proportions. Residential layouts repeat familiar arrangements. Public structures display common planning principles. Such consistency suggests the existence of skilled professional builders working within shared traditions. Yet virtually no technical manuals survive. Unlike Roman engineering, which left behind texts such as those attributed to Vitruvius, the practical knowledge behind Surkania's construction methods appears largely lost. The buildings remain, but the instructions disappeared. Located along the Thach Han River in central Vietnam, Quang Tri's citadel was constructed during the Nguyen dynasty in the early 19th century. At first glance, it seems to be a typical military fortress, but researchers have uncovered a far more compelling story beneath its walls. As archaeologists, engineers, and historians continue to study the site, they face an increasingly difficult question. How did its builders successfully combine European military engineering, local construction methods, sophisticated water management, and large-scale logistics in an environment that was far from ideal for such an undertaking? Unlike many historical mysteries centered on massive stone monuments, the mystery of Quang Tri is rooted in knowledge itself, a body of expertise that enabled engineers to create a durable fortress on unstable floodplain terrain, while leaving behind remarkably few records explaining exactly how they achieved it. The citadel was established during the reign of Emperor Jia Long and later expanded under Emperor Min Mang as part of a defensive network protecting central Vietnam. Historical documents identify it as a Vauban-style fortress, a military design originally developed in 17th century France by the famous engineer Sébastien Leprestre de Vauban. The discovery is not the fortress itself, which has always been visible, but the realization by modern researchers that many aspects of its construction remain poorly understood. Surveys, excavations, historical maps, and structural studies have revealed engineering challenges far greater than previously assumed. The first mystery begins with the ground beneath the fortress. Quangtree sits on alluvial terrain formed by centuries of river deposition. Modern geotechnical engineers generally consider such environments problematic for large defensive structures because soft sediments compress under heavy loads, causing differential settlement and structural instability. Yet the original fortress occupied an area measuring roughly 16 hectares and was surrounded by extensive ramparts and moats. The mass of earth, brick, and stone involved would have placed enormous pressure on the underlying soil. Even today, engineers constructing large projects on similar terrain frequently rely on deep foundations, reinforced concrete piles, soil stabilization systems, and sophisticated geotechnical analysis. The Nguyen engineers possessed none of these technologies. Nevertheless, the citadel remained structurally viable for generations. Researchers continue debating how the builders stabilized the foundation. Some theories suggest the use of compacted earth layers combined with carefully selected fill materials. Others point toward possible timber reinforcement systems similar to those employed elsewhere in Southeast Asia. Comparable techniques have been documented beneath parts of the imperial city of Hue, where wooden piles were driven into saturated ground to distribute structural loads. However, definitive evidence for the exact methods used at Quangtree remains limited. The result is a paradox. The fortress existed in a location where modern engineers would immediately recognize significant geotechnical risks. Yet, its builders successfully created a durable defensive installation long before soil mechanics became a scientific discipline. Water management presents another puzzle. The citadel was surrounded by a defensive moat integrated into the regional hydrological system. Maintaining such a moat sounds straightforward until the local climate is considered. Quangtree experiences some of the most extreme weather conditions in Vietnam. Annual rainfall often exceeds 2,000 millimeters, with intense monsoon events capable of producing severe flooding. Excess water threatens to erode embankments, undermine foundations, and fill defensive structures with sediment. Conversely, dry season conditions can reduce water levels and compromise defensive effectiveness. Modern hydraulic engineers solve these challenges using computer models, controlled sluice gates, and detailed hydrological monitoring. The builders of Quangtree had none of these tools, yet historical descriptions suggest the moat system functioned effectively for decades. Researchers suspect the existence of carefully engineered channels connecting the fortress to nearby waterways, allowing controlled regulation of water levels. Unfortunately, much of the original hydraulic infrastructure has been altered, damaged, or lost, making reconstruction difficult. What survives is evidence that the engineers understood practical hydrology at a level that exceeds what surviving documentation can explain. The walls themselves introduce another technical mystery. Unlike European stone fortresses, Quangtree relied heavily on brick and earth construction. This choice may appear less impressive than massive masonry walls, but materials scientists often note that earthen and brick fortifications can perform surprisingly well against artillery because they absorb and dissipate energy rather than shattering catastrophically. The question is how Nguyen engineers optimize these materials. The climate of central Vietnam is exceptionally destructive. High humidity, tropical heat, biological growth, seasonal flooding, and salt transport from coastal winds accelerate deterioration. Many structures built under such conditions require constant maintenance. Yet portions of the original citadel survived not only environmental stress, but also one of the most intense bombardments in modern military history during the Battle of Quang Tri in 1972. Tens of thousands of artillery shells, aerial bombs, and explosive impacts struck the area over an 81-day period. Although the fortress suffered immense damage, significant portions remained identifiable afterward. This raises an intriguing engineering question. Were the original construction materials inherently more resilient than modern researchers assume? Laboratory studies of historical mortars throughout Asia have repeatedly demonstrated that ancient builders often employed sophisticated mixtures incorporating lime, clay, plant fibers, organic additives, and locally sourced minerals. Some traditional mortars exhibit mechanical properties difficult to reproduce precisely today. Similar mysteries have emerged in studies of Roman marine concrete, whose durability continues to attract scientific attention nearly 2,000 years after its creation. Quang Tri may preserve evidence of comparable material knowledge, though the original formulations remain largely unknown. Perhaps the most fascinating mystery concerns geometry and surveying. Vauban-style fortifications are not random collections of walls. Their effectiveness depends upon carefully calculated angles, designed to eliminate blind spots and maximize defensive fields of fire. Every bastion, curtain wall, and moat must align with a broader geometric plan. Modern military engineers accomplish such tasks using precision instruments, digital mapping systems, satellite positioning, and advanced mathematical models. The builders of Quang Tri relied on methods available in early 19th century Vietnam. Despite these limitations, aerial imagery reveals a remarkably coherent geometric layout. Researchers continue investigating how surveyors established accurate alignments across the site. Did they employ astronomical observations? Were specialized measuring techniques imported through contact with European military advisors? Or had local traditions of surveying already achieved a level of precision sufficient for such projects? The historical record provides only partial answers. The mystery deepens when Quang Tri is compared with other Nguyen fortifications. Fortresses at Hue, Vinh, Bac Ninh, and elsewhere demonstrate a remarkable consistency in planning principles. This suggests the existence of a broader technical tradition operating across the empire. Such standardization required training, knowledge transfer, and engineering administration on a scale rarely discussed in popular histories of Vietnam. Somehow, complex military architecture was being reproduced across large distances with a degree of consistency that implies sophisticated institutional knowledge. Near the modern border between Georgia and Abkhazia, a fortress overlooks the lowlands of western Georgia not far from the Black Sea. For decades, archaeologists, historians, and military engineers have studied this stronghold, yet the more closely they examine its surviving walls, the more challenging a fundamental question becomes. How did builders working centuries before modern engineering create a defensive complex capable of resisting earthquakes, floods, artillery bombardment, and environmental decay in one of the most demanding landscapes of the Caucasus? The fortress first drew serious scholarly attention through historical surveys of the Samegrelo region, where researchers documented the remains of massive stone walls, defensive towers, and fortifications associated with the Principality of Mingrelia. Historical records identify Ruki as an important military stronghold during conflicts between local Georgian rulers and the Ottoman Empire in the 17th and 18th centuries. Yet documents explain why the fortress was built far more clearly than they explain how it was built. The surviving structure presents a series of engineering puzzles that continue to attract attention from archaeologists and military historians. The first mystery begins with location. Modern engineers generally avoid placing large masonry fortifications on low-lying terrain exposed to seasonal flooding and unstable soils. The region surrounding Rukki receives substantial annual rainfall influenced by the Black Sea climate. Nearby rivers periodically alter local hydrology, creating conditions that can destabilize foundations over time. Yet the fortress stood for centuries despite these environmental pressures. Stone fortifications weighing thousands of tons normally suffer differential settlement when constructed on weak ground. Even a few centimeters of uneven movement can produce cracks capable of propagating through entire walls. Surprisingly, large portions of Rukki remained structurally stable, long enough to survive warfare, abandonment, and natural erosion. Researchers still debate whether builders employed foundation techniques now lost to history or whether they possessed an exceptionally sophisticated understanding of local geology acquired through generations of observation. The walls themselves introduce another challenge. Rukki emerged during an era when gunpowder warfare had transformed military architecture throughout Europe and Western Asia. Medieval castles designed for arrows and siege ladders often became obsolete once heavy artillery appeared. Across Europe, engineers responded by developing star forts, angular bastions, thicker ramparts, and complex defensive geometries capable of dispersing cannon fire. Rukki was not a classic European star fort, yet certain aspects of its construction suggest that its builders understood many of the same principles. Defensive walls appear unusually robust for a regional fortress. Their thickness and arrangement indicate an awareness that stone structures must absorb and redistribute impact energy rather than merely resist it. Modern structural analysis demonstrates that wall thickness can dramatically influence survivability under bombardment by reducing stress concentrations and delaying catastrophic failure. The question is how local engineers developed such practical knowledge without access to formal engineering schools, mathematical modeling, or modern materials science. The geometry of the fortress presents an equally intriguing puzzle. At first glance, the layout seems irregular compared with the highly symmetrical fortifications of Renaissance Europe. Closer examination suggests that the apparent asymmetry may actually represent optimization. Military engineers today frequently modify defensive layouts to account for terrain, lines of sight, artillery range, and potential avenues of attack. Rukki appears to have been adapted carefully to its surroundings. Certain wall alignments maximize visibility across approaches to the fortress, while minimizing blind spots. Some towers occupy positions that provide overlapping fields of observation. Such planning required accurate surveying despite the absence of laser instruments, satellite imagery, aerial photography, or modern cartography. Ancient and medieval surveyors could certainly achieve impressive results, but Rukki raises questions about the precision attainable through traditional methods alone. Perhaps the most overlooked mystery concerns water management. Every fortress faces a paradox. Defenders require access to water, yet water is also one of architecture's greatest enemies. Moisture weakens foundations, accelerates erosion, damages mortar, and increases structural instability. In wet climates, the challenge becomes even greater. Modern engineers employ drainage systems, retaining structures, groundwater controls, and hydrological modeling to protect major buildings. The continued survival of portions of Rukki implies that its builders developed effective solutions to these same problems. Archaeological evidence suggests that drainage and site management played important roles in maintaining the fortress. Unfortunately, many original hydraulic features have disappeared, leaving researchers to reconstruct them indirectly from surviving remains. The result is a technological mystery hidden beneath the visible architecture. The materials used in construction create another unanswered question. Across the ancient world, scientists continue investigating historic mortars that display extraordinary durability. Roman marine concrete remains one of the most famous examples. Laboratory studies have shown that certain Roman mixtures actually strengthened over time through chemical reactions involving seawater and volcanic minerals. Although Ruki was built in a different era and cultural context, the fortress demonstrates similar questions regarding long-term material performance. Portions of the masonry have survived centuries of environmental exposure, despite repeated cycles of moisture, heat, freezing temperatures, and biological weathering. Researchers know the general ingredients employed in traditional Caucasian construction, yet the precise formulation, preparation methods, curing processes, and quality control practices used at Ruki remain poorly documented. The possibility that builders possess specialized material knowledge transmitted through craft traditions, but never recorded in writing, remains an active subject of interest. Logistics may represent the greatest engineering challenge of all. Every stone visible in the fortress had to be quarried, shaped, transported, lifted, and positioned without modern machinery. Even conservative estimates suggest that the total mass of material involved reached tens of thousands of tons. Today, cranes, trucks, hydraulic equipment, and computer-guided planning make such projects routine. In the 17th and 18th centuries, every stage depended upon human labor, animal power, and mechanical systems constructed from wood, rope, and iron. Moving a single large stone block can require dozens of workers. Constructing an entire fortress requires coordination on an entirely different scale. Historical records reveal political and military motivations for building Ruki, but provide only fragmentary insight into the organizational systems that transformed raw materials into a functioning defensive complex. This gap in knowledge leaves archaeologists confronting a familiar problem found throughout the ancient world. The monument survives, but the process that created it has largely vanished. Comparisons with other fortifications make the puzzle even more compelling. The great bastioned fortresses of France designed by Vauban relied upon advanced geometric planning and state-level resources. Ottoman frontier fortifications benefited from extensive imperial logistics. Massive Caucasian strongholds such as Narikala and other regional fortresses occupied naturally defensible terrain that reduced engineering demands. Ruki, by contrast, appears to combine difficult environmental conditions with substantial defensive ambitions. It was neither among the largest fortresses of its era nor among the most famous, yet its survival suggests a level of technical competence often overlooked in discussions of military architecture. Perched on a rocky ridge northwest of Glasgow, Scotland, Mugdock Castle appears at first glance to be just another medieval ruin. Yet archaeologists and engineers have long been fascinated by a simple question. How has a fortress first established in the 14th century survived on such a challenging landscape for hundreds of years despite warfare, harsh weather, structural collapse, and centuries of neglect? The mystery emerged through archaeological surveys, architectural studies, and conservation investigations conducted across the ruins of the stronghold. What researchers uncovered was far more than the remains of an ordinary Scottish castle. Hidden within its surviving walls are engineering decisions that continue to raise questions about medieval knowledge of geology, structural stability, water management, and defensive design. The history of Mugdock Castle is closely connected to the powerful Graham family, one of Scotland's most influential noble dynasties. The earliest stone structures are generally dated to the 14th century, although modifications continued for centuries afterward. Today, much of the castle lies in ruins, yet enough remains to reveal remarkable technical achievements. What makes the site particularly intriguing is that medieval builders worked without modern surveying instruments, structural calculations, reinforced concrete, or geological mapping. Nevertheless, the fortress remained functional for generations in an environment that should have accelerated its destruction. One of the first puzzles involved the castle's foundations. Modern engineers understand that the long-term survival of any large stone structure depends heavily on the quality of the ground beneath it. Scotland presents unique challenges. Seasonal rainfall can exceed 1,000 millimeters annually in some regions. Freeze-thaw cycles repeatedly expand and contract moisture trapped within stone and soil. Over centuries, these processes can fracture masonry and destabilize foundations, yet significant portions of Mugdock remain standing long after many comparable structures collapsed. Geological studies indicate that the castle occupies a landscape composed of varying rock formations and weathered materials, rather than a perfectly uniform platform. Such conditions normally increase the risk of differential settlement, where one section of a structure sinks faster than another. Even a few centimeters of uneven movement can create cracks that eventually threaten an entire building. Medieval builders possessed no modern geotechnical equipment, yet they somehow selected locations capable of supporting massive masonry walls. Researchers continue debating whether this success resulted from accumulated empirical knowledge, generations of construction experience, or a sophisticated practical understanding of local geology that was never recorded in written form. The surviving masonry introduces another mystery. Castle walls in medieval Scotland often exceeded 2 meters in thickness, and some defensive towers contained even larger stone masses. At Mugdock, portions of these structures have endured hundreds of years of environmental stress. Modern conservation specialists studying historic fortifications frequently encounter an unexpected phenomenon. Ancient masonry sometimes performs better than predicted by contemporary models. Stones settle into stable load paths, allowing enormous weights to redistribute naturally throughout the structure. While modern engineers can describe these mechanisms mathematically, medieval builders lacked such equations. The question therefore becomes how accurately they understood structural behavior through observation alone. Similar mysteries appear at major European fortifications such as the castles of Wales, built under King Edward I, or the massive Norman keeps scattered across Britain. In each case, builders repeatedly achieve stability that would normally require extensive calculations. Mugdock provides a smaller but equally intriguing example of this phenomenon. Every surviving wall represents evidence of knowledge that functioned effectively, even if its theoretical basis remains unknown. The geometry of the castle deepens the puzzle. Medieval surveying was far more difficult than many people realize. Establishing straight walls, right angles, consistent elevations, and aligned defensive positions across uneven terrain requires precision. Today, such tasks are accomplished using laser levels, total stations, satellite positioning systems, and computer modeling. 14th century builders relied primarily on ropes, measuring rods, plumb bobs, and experience. Yet architectural surveys reveal surprisingly accurate alignments throughout surviving sections of the fortress. Small errors introduced during construction could have multiplied dramatically as walls rose higher. Instead, many medieval structures demonstrate a level of geometric control that continues to impress specialists. Historians often attribute this success to master masons who transmitted practical knowledge through apprenticeships. However, almost no detailed technical manuals survive explaining exactly how these methods were performed. The structures remain, but much of the process behind them has disappeared. Defensive engineering creates another layer of mystery. Mugdock was not among the largest castles in Scotland, yet its position offered significant strategic advantages. Medieval military architecture increasingly relied on maximizing terrain, rather than simply constructing larger walls. The castle exploited elevated ground, restricted approaches, and overlapping fields of observation. Modern military analysts would describe this as force multiplication, using geography to increase defensive effectiveness without dramatically increasing manpower. What remains unclear is how builders evaluated these advantages before construction began. Medieval commanders lacked aerial photography, topographic mapping software, and computer simulations. Nevertheless, many castles consistently occupy positions that maximize visibility, control movement corridors, and reduce vulnerability. The same pattern appears from Scotland to France, Germany, and Eastern Europe. Mugdock contributes another example of an ancient problem-solving process whose details have largely vanished from history. Water management may represent the most underestimated technological mystery of all. Every fortress ultimately depends on reliable access to water. During a siege, food shortages can sometimes be endured for weeks or months, but water shortages become critical much sooner. Historians estimate that even a relatively small garrison could require thousands of litres of water each week for drinking, cooking, sanitation, and livestock. The original hydraulic systems of Mugdock are no longer fully preserved, leaving archaeologists with an incomplete picture. Questions remain regarding rainwater collection, storage capacity, drainage channels, and groundwater access. Effective drainage is particularly important because water trapped near foundations accelerates structural deterioration. Modern civil engineers devote enormous effort to controlling moisture around buildings. Medieval builders lacked contemporary hydrological science, yet many castles demonstrate surprisingly effective water management. Whether this knowledge emerged through trial and error or through highly developed practical engineering remains uncertain. Environmental adaptation presents an equally fascinating challenge. The climate of Western Scotland is notoriously demanding. High humidity, frequent storms, strong winds, and fluctuating temperatures place continuous stress on masonry. Modern building materials often require significant maintenance under such conditions. Yet medieval castles were expected to function for generations. Researchers studying historic stone structures increasingly recognize that ancient builders may have possessed an exceptional understanding of local materials. Stone selection was not random. Different rock types vary dramatically in compressive strength, porosity, resistance to weathering, and susceptibility to freeze-thaw damage. Choosing inappropriate materials could shorten a structure's lifespan by centuries. At Mugdock, as at many surviving medieval fortifications, the enduring sections may reflect careful decisions regarding quarry selection and stone placement that remain only partially understood today. On the Indian Ocean coast near modern Dar es Salaam, Tanzania, stands a remarkable archaeological site that seems unlikely to have survived in such a harsh environment. Salt-laden winds, tropical humidity often exceeding 70%, seasonal monsoon rains, and centuries of coastal erosion create one of the most destructive settings for ancient architecture. Yet fragments of walls, mosque foundations, tombs, and stone structures have endured for hundreds of years. The ruins appear modest compared to famous sites such as Machu Picchu, Petra, or Angkor. However, beneath their weathered appearance lies a technological mystery that continues to challenge archaeologists, engineers, and material scientists studying the ancient Swahili civilization. The site became known through colonial-era surveys and later archaeological investigations conducted throughout the 20th century. Excavations revealed evidence of a thriving settlement connected to the wider Swahili trading world between approximately the 10th and 16th centuries. Imported ceramics from China, glassware from the Middle East, and trade goods from India demonstrated that Kunduchi participated in an international commercial network stretching thousands of kilometers across the Indian Ocean. Yet the imported objects were not the most surprising discovery. What attracted scientific attention was the architecture itself. Researchers began asking a question that remains only partially answered today. How did local builders create structures capable of surviving for centuries in an environment that rapidly destroys most construction materials? The mystery begins with the stone itself. Most of the buildings at Kunduchi were constructed using coral rag, a limestone material formed from ancient coral reefs. To modern engineers, coral stone presents obvious challenges. It is porous, relatively soft compared to granite, and highly vulnerable to salt penetration. In coastal environments, salt crystals expand and contract inside microscopic pores, gradually breaking stone apart. This process, known as salt weathering, is one of the primary causes of architectural deterioration in marine climates. Yet many coral stone structures along the Swahili coast, including those at Kunduchi, have endured for hundreds of years. The survival of these structures suggests that ancient builders possessed a sophisticated understanding of material selection. Geological studies indicate that not all coral stone was used equally. Certain sections display higher density and greater resistance to weathering than others. Modern laboratory testing shows that variations in porosity can dramatically affect long-term durability. The builders appear to have recognized these differences centuries before geology became a scientific discipline. The question is how? No written manuals survive explaining how quarry workers identified suitable stone. No technical texts describe quality control procedures. Yet the evidence suggests that generations of craftsmen developed a practical material science based entirely on observation and experience. Even more remarkable is the substance binding the stones together. Among all the technological mysteries surrounding Kunduchi, none is more fascinating than the lime mortar. In many locations throughout the ruins, the mortar remains surprisingly intact despite centuries of exposure to moisture, temperature fluctuations, biological growth, and marine salt. Under normal circumstances, traditional lime mortar deteriorates steadily in tropical coastal environments. Modern conservation projects frequently struggle to achieve even a few decades of durability under similar conditions. Yet some of Kunduchi's mortar joints have survived for more than 500 years. Scientific analysis indicates that Swahili builders produced lime by burning coral limestone at high temperatures. This process converts calcium carbonate into quicklime. Water is then added to create slaked lime, which can be mixed into mortar. The chemistry itself is well understood today. What remains unclear is why the resulting material performed so exceptionally well. Researchers have proposed several explanations. One possibility involves extended lime maturation. Historical records from other regions show that some ancient builders aged lime for months or even years before use. Longer maturation can improve workability, reduce cracking, and enhance durability. Another theory suggests the addition of organic materials. Around the ancient world, builders mixed substances such as plant extracts, oils, animal products, or fibers into construction mortars. Roman engineers famously incorporated volcanic ash into concrete, creating structures that remain intact after 2 millennia. In parts of China, sticky rice was added to lime mortar, increasing strength and water resistance. Scientists studying Kunduchi have wondered whether a similar local additive may once have been used, but has since disappeared from the archaeological record. Microscopic examinations reveal complex mineral transformations occurring within the mortar over centuries. As carbon dioxide from the atmosphere slowly reacts with lime, new crystalline structures form. Some researchers believe these processes may have created a self-strengthening effect that enhanced durability over time. Others argue that the exceptional performance resulted from precise ratios between lime, sand, and crushed coral aggregates. The challenge is that no surviving document records the original formula. The builders left behind the product, but not the recipe. Consequently, modern conservation specialists can observe the results without fully understanding the manufacturing process. This uncertainty becomes even more intriguing when comparisons are made with other ancient engineering traditions. Roman marine concrete continues to puzzle scientists because it grows stronger through reactions with seawater. Certain medieval cathedrals in Europe contain mortars whose production methods are still debated. The Swahili coast may represent another example of lost material technology. If so, Kunduchi preserves evidence of a construction science that has largely vanished from history. The architectural orientation of the site introduces another mystery. Several religious structures demonstrate careful alignment toward Mecca. Today, determining the Qibla direction requires only a smartphone application or GPS receiver. Medieval builders possessed neither. From East Africa to the Arabian Peninsula lies a distance of roughly 3,000 kilometers. Achieving accurate orientation across such distances requires knowledge of geography, astronomy, and measurement techniques. Many scholars believe Swahili navigators utilize celestial observations similar to those employed by Indian Ocean sailors. Long before modern navigation systems, mariners crossed vast stretches of ocean using stars, seasonal winds, and solar positioning. Historical accounts describe navigators memorizing star paths and horizon angles with remarkable precision. If similar methods were employed on land, they could explain the orientation of Kunduchi's mosques. Yet no direct evidence has revealed exactly how builders translated navigational knowledge into architectural layouts. Water management presents another engineering puzzle. Establishing a permanent settlement near the ocean requires reliable access to fresh water. Coastal aquifers frequently suffer from saltwater intrusion, particularly in low-lying regions. Archaeological surveys have identified wells and water collection systems associated with Swahili settlements. However, researchers remain uncertain how communities such as Kunduchi maintain sustainable freshwater supplies over centuries. Hydrological studies suggest that successful water extraction would have required detailed understanding of local geology. Wells positioned only a short distance apart can produce dramatically different results depending on underground conditions. Modern engineers rely on geological mapping, drilling surveys, and hydrological models. Ancient communities relied on accumulated experience. The placement of water infrastructure at Kunduchi hints at environmental knowledge far more sophisticated than often assumed for medieval coastal settlements. Trade likely contributed to Kunduchi's technological achievements. Archaeological evidence shows links between East Africa, Arabia, Persia, India, and China, where merchant ships carried both goods and ideas. Through these networks, construction techniques, navigation skills, and material innovations could spread across regions. However, it remains unclear whether Kunduchi's engineering solutions were imported or developed locally. Most likely, they were a combination of both. Swahili builders adapted outside influences to local conditions, creating a distinctive architectural tradition suited to East Africa's coastal environment. Nisa, located at the foothills of the Kopet Dag Mountains in present-day Turkmenistan, was never meant to become one of archaeology's greatest technological mysteries. Founded more than 2,000 years ago as an early royal centre of the Parthian Empire, the site appears at first glance to be another ruined fortress of mud brick and earth. Yet the deeper archaeologists investigate Nisa, the more difficult it becomes to explain how a civilization often overshadowed by Rome and Persia, developed engineering solutions that continue to puzzle researchers today. Hidden within its walls are clues to lost construction techniques, advanced materials science, environmental engineering, and artistic technologies that seem far ahead of what many historians once believed possible. The discovery of Nisa was gradual rather than dramatic. Travelers had reported ancient ruins in the region for centuries, but systematic archaeological excavations began during the 20th century, particularly under Soviet expeditions. As excavators uncovered fortifications, ceremonial halls, warehouses, sculptures, ivory artifacts, and administrative buildings, they realized they were looking at one of the most important centers of the Parthian world. What emerged from the sands was not simply a royal residence, but an entire laboratory of ancient engineering. The first mystery appears in the massive defensive walls surrounding Old Nisa. Even today, portions of these fortifications survive despite being constructed primarily from mud brick and rammed earth. Archaeological studies suggest that some walls originally exceeded 10 meters in height and several meters in thickness. Such structures should have been highly vulnerable to erosion. Modern engineers know that earthen architecture faces constant threats from rainfall, groundwater, temperature fluctuations, wind abrasion, and seismic activity. Yet significant sections of Nisa survived for more than 2 millennia. Comparisons with other ancient earthen cities make the achievement even more remarkable. Many settlements throughout Central Asia, Mesopotamia, and North Africa suffered severe degradation within centuries when maintenance ceased. Nisa, however, preserved substantial architectural remains long enough for modern excavation. Researchers continue to debate whether the Parthians possessed specialized knowledge regarding soil composition, moisture control, compaction methods, or organic stabilizing additives. Laboratory analyses reveal carefully selected mixtures of clay, sand, and mineral inclusions, but the exact construction recipes remain uncertain. The walls appear to represent a level of material optimization that ancient builders achieved without modern geology or engineering theory. The layout of Nisa presents another challenge. Satellite imagery and archaeological surveys reveal an unexpectedly organized urban plan. Defensive walls follow remarkably consistent alignments. Major structures appear arranged according to deliberate geometric principles. Achieving such precision would be impressive even with modern surveying tools. Yet Parthian engineers lacked laser instruments, optical levels, electronic measurements, and modern cartography. Ancient surveyors elsewhere often relied on ropes, measuring rods, sighting poles, and astronomical observations. Egyptian pyramid builders, Roman military engineers, and Greek architects all developed sophisticated methods for maintaining geometric accuracy. The question is whether the Parthians independently reached comparable levels of precision or inherited knowledge from earlier traditions. Some researchers argue that Nisa demonstrates a degree of planning, suggesting highly trained specialists whose technical knowledge has largely vanished from the historical record. Environmental engineering presents another puzzle. Nisa existed in a region where summer temperatures can exceed 40 degrees Celsius. Water availability was limited, and seasonal conditions could be extreme. Maintaining food supplies, ceremonial goods, and administrative functions under such circumstances required effective climate management. Excavations uncovered enormous storage vessels capable of holding hundreds of liters of liquid or grain. These containers were housed within carefully designed storage complexes. Modern studies of thermal dynamics suggest that thick earthen walls can moderate internal temperatures through thermal mass, absorbing heat during the day and releasing it slowly at night. The builders of Nisa appear to have exploited these principles long before scientists understood the physics involved. Some researchers have even compared aspects of ancient passive cooling systems to modern sustainable architecture. Yet exactly how these facilities maintained stable conditions throughout the year remains incompletely understood. Another mystery emerges from the architectural remains of ceremonial halls and elite structures. Evidence suggests that some buildings incorporated large enclosed spaces requiring substantial structural support. Reconstructing these roofs has proven difficult because most superstructures collapsed long ago. Some archaeologists propose sophisticated vaulting or roofing systems capable of spanning considerable distances. Others suggest combinations of timber frameworks and mud brick reinforcement. The challenge is that surviving evidence supports multiple interpretations. Computer simulations demonstrate several possible engineering solutions, but no consensus exists regarding which method Parthian builders actually employed. The disappearance of critical structural elements means that one of the most important chapters of Parthian architecture may remain permanently incomplete. Yet perhaps the most fascinating mystery of Nysa concerns not its walls or storage systems, but its extraordinary artistic technology. Excavators uncovered evidence of monumental clay sculptures that once decorated ceremonial buildings. Fragments reveal figures larger than life-size, constructed from carefully modelled clay and coated with sophisticated surface treatments. At first, these statues appeared similar to other ancient sculptural traditions. Closer examination, however, revealed a technological puzzle. Creating giant clay statues is far more complicated than producing small figurines. Large sculptures face severe structural stresses. Their weight can cause cracking during drying. Internal moisture gradients generate tension. Thermal expansion and contraction create additional instability. Modern ceramic engineers understand these challenges well. Ancient artisans at Nysa somehow overcame many of them. Analysis of surviving fragments indicates careful control over clay composition, particle size, and construction methods. Certain pieces display evidence of layered manufacturing techniques that reduced stress concentrations. Some researchers believe internal support systems may have existed, although definitive proof remains elusive. The precision of the modelling suggests not merely artistic talent, but an advanced understanding of material behaviour. Even more mysterious is the surface technology applied to these statues. Many fragments preserve traces of plaster coatings that remained attached despite centuries of environmental exposure. These coatings were not simple decorative layers. They served as engineered surfaces capable of creating smooth finishes, supporting pigments and protecting underlying structures. Laboratory examinations reveal multiple preparation stages. Fine plaster layers were applied over carefully prepared substrates. In some cases, pigments adhered remarkably well despite the passage of more than 2,000 years. The durability of these finishes continues to surprise conservators. Comparisons with other ancient traditions are revealing. Greek marble sculpture relied on stone permanence. Roman statues often used marble or bronze. The famous terracotta army of China employed highly controlled firing technologies. Nysa represents a different approach entirely. Parthian craftsmen transformed fragile clay into monumental works capable of surviving centuries. The exact formulas used in the plaster coatings remain only partially understood. Modern conservation teams can identify mineral components, but reconstructing the complete manufacturing process remains challenging. Some specialists argue that the coatings may have incorporated carefully selected gypsum mixtures, organic binders, or locally sourced mineral additives. Others suggest that application techniques played a greater role than chemical composition. The debate continues because the surviving evidence remains incomplete. Every new fragment recovered from Nysa has the potential to alter existing theories. The famous ivory write-ons discovered at Nysa introduce another technological question. These ceremonial vessels display extraordinary craftsmanship and microscopic detail. Carved from imported ivory, they demonstrate levels of precision comparable to elite luxury objects from the Hellenistic world. Producing such works required specialized tools, controlled workshops, and highly trained artisans. Yet, almost no written records explain how these workshops operated. On a small coral island off the southern coast of present-day Tanzania, a city rose to become one of the greatest urban centers of medieval Africa, despite conditions that seemed to make such success impossible. Surrounded by salt water, lacking major freshwater sources, and exposed to centuries of tropical storms, erosion, humidity, and sea spray, Kilwa Kisiwani appeared destined to fade away. Yet its ruins still stand, with massive walls remaining upright, vaulted ceilings surviving, and ancient mosques revealing a level of engineering sophistication that challenges many assumptions about the technological capabilities of East Africa 1,000 years ago. The deeper archaeologists investigate Kilwa, the more difficult it becomes to explain how civilization on a remote island transformed itself into one of the wealthiest trading powers of the Indian Ocean, while mastering construction techniques that remain only partially understood today. Unlike many ancient cities that vanished beneath jungles or deserts, Kilwa was never completely forgotten. Medieval Arab geographers described it as one of the richest ports in the world, while Portuguese explorers arriving in the early 16th century recorded impressive stone buildings, palaces, mosques, and thriving commercial districts. Systematic archaeological investigations began during the 20th century, revealing the remains of a city that flourished between approximately the 11th and 15th centuries. Excavations uncovered imported Chinese porcelain, Persian ceramics, Indian beads, Arabian glassware, and thousands of local artifacts. These discoveries confirm that Kilwa was not a peripheral settlement, but a major participant in an international trade network stretching more than 8,000 kilometers across the Indian Ocean. Yet the imported goods told only part of the story, as the real mystery emerged from the buildings themselves. The first challenge facing any settlement of Kilwa Island was obvious. There was almost no conventional building stone. The island consists primarily of coral limestone formations, created by marine organisms over thousands of years. Coral limestone is relatively lightweight and easy to cut when freshly quarried, but it's also porous, brittle, and vulnerable to environmental damage. Modern engineers generally avoid relying exclusively on such materials for large, long-lasting structures exposed to marine environments. Yet the builders of Kilwa did exactly that. The Great Mosque of Kilwa, first established around the 11th century and expanded repeatedly over centuries, became one of the largest stone structures in sub-Saharan Africa. Nearby stood Husuni Kubwa, a palace complex covering roughly 2 acres and containing more than 100 rooms. Massive walls, arches, domes, courtyards, and storage facilities were all constructed using locally available coral stone. What remains difficult to explain is not merely the existence of these structures, but their survival. Modern coastal concrete often suffers severe deterioration within decades because salt water penetrates microscopic cracks, corrodes internal components, and weakens structural integrity. Kilwa's coral buildings have endured for centuries despite continuous exposure to harsh marine conditions, suggesting that the builders possessed a much deeper understanding of material behavior than traditionally assumed. Among all the engineering puzzles of Kilwa, none is more fascinating than the mortar. The construction process appeared deceptively simple. Coral blocks were quarried from reefs and fossilized deposits, while other coral material was burned in kilns at temperatures estimated between 800 and 1,000 degrees Celsius to produce lime. This lime was then mixed with water and aggregates to create mortar. On the surface, this resembles countless lime-based construction traditions across the ancient world. However, laboratory studies of surviving Kilwa mortar reveal unusual characteristics. Many joints remain remarkably intact despite centuries of moisture infiltration, and some sections display levels of cohesion far exceeding what archaeologists would normally expect from medieval lime mortar exposed to tropical coastal conditions. Researchers have observed evidence suggesting that chemical reactions continued long after construction was completed. Over time, dissolved minerals from seawater may have interacted with lime compounds inside the mortar matrix, creating new crystalline structures that strengthened the material rather than weakening it. This phenomenon invites comparisons with Roman maritime concrete. The Romans famously used volcanic ash known as pozzolana to create harbour structures capable of surviving nearly 2 millennia, and scientific studies have shown that seawater gradually generated new mineral formations within Roman concrete, increasing its durability over time. Kilwa lacked access to Mediterranean volcanic ash, yet its builders appear to have achieved a surprisingly similar outcome through entirely different materials. The question remains unresolved. Did Kilwa's masons intentionally engineer mortar chemistry to exploit marine mineralization processes? Or did generations of experimentation accidentally produce one of the most durable construction materials in medieval Africa? No surviving written manuals explain the formula, and the technology vanished while the buildings endured. Freshwater may have been an even greater challenge than construction. Coral islands generally struggle to retain fresh water because rainwater rapidly infiltrates porous limestone, while seawater intrusion threatens underground reserves. Sustaining a large urban population under such conditions requires sophisticated environmental management. Archaeological surveys have identified cisterns, reservoirs, drainage systems, and water collection facilities integrated throughout Kilwa's architecture. Some structures appear specifically designed to capture seasonal rainfall and reduce evaporation losses. The scale of the problem is significant. Historical estimates suggest that Kilwa supported thousands of inhabitants during its peak, and even a population of 5,000 people would require millions of litres of fresh water annually for drinking, cooking, sanitation, and industrial activities. Yet no major river existed on the island. Researchers continue debating how the city maintained reliable water supplies across generations. Some propose extensive rainwater harvesting systems, while others suggest careful management of freshwater lenses trapped beneath the island's surface. Neither explanation fully accounts for the city's long-term sustainability. The engineering knowledge required to solve this challenge may represent one of Kilwa's greatest lost technologies. The Great Mosque contains clues pointing towards sophisticated geometric knowledge. Visitors often focus on its historical significance, but engineers notice something different. Arches distribute loads efficiently across walls. Vaulted spaces create large interior volumes while minimizing structural stress, and domes require careful understanding of force distribution and weight transfer. These features are not impossible to create through trial and error. However, achieving them repeatedly and successfully across centuries implies accumulated technical knowledge. The builders lacked modern mathematics, computer modeling, or structural analysis software. Nevertheless, they produced architectural forms that obey the same physical principles used in contemporary engineering. Some scholars argue that these techniques arrived through contact with Persian and Arabian builders, while others believe local Swahili craftsmen adapted imported ideas and transformed them into uniquely regional solutions. The surviving evidence suggests a combination of both influences, but the exact process remains uncertain. Along the coastal mountains of western Syria, between dense valleys and the winds coming from the Mediterranean Sea, stands one of the least discussed yet most technically mysterious ancient complexes in the Levant, Hosn Suleiman. Unlike Petra, Palmyra, or Baalbek, Hosn Suleiman rarely appears in mainstream documentaries, yet the site contains engineering features that continue to puzzle archaeologists, structural engineers, and historians alike. Massive stone platforms still stand on unstable mountainous terrain. Precision-cut masonry survives in an earthquake zone. Drainage systems continue to function after nearly 2,000 years, and beneath the visible ruins may lie entire underground sections that modern excavation has barely touched. The first modern documentation of the site began during surveys conducted in the 19th century under Ottoman-era exploration campaigns. At first, researchers believed the ruins were simply remnants of a regional Roman sanctuary dedicated to local deities. But each new excavation complicated that theory. Archaeologists uncovered massive retaining walls far larger than necessary for a simple mountain temple. They found unusually thick foundations buried beneath later Roman additions. Then came the discovery of strange underground chambers carved directly into bedrock, suggesting the complex may once have served purposes far beyond religion. One of the earliest mysteries emerged from the location itself. Hosn Suleiman was built at an elevation where transporting construction material would have been extraordinarily difficult. Some limestone blocks used in the platform and lower walls weigh several tons each. Even today, moving stones of that size through steep mountain terrain would require cranes, engineered roads, and hydraulic systems. Yet ancient builders somehow achieved this nearly 2,000 years ago using only primitive transport technology. The puzzle becomes even stranger when compared to other mountain complexes of the ancient world. At Machu Picchu in Peru, Inca engineers used carefully cut stones fitted together without mortar to survive earthquakes. At Hosn Suleiman, researchers discovered a surprisingly similar concept. Several wall sections appear designed with slight movement tolerance between blocks. Instead of rigidly locking every stone into place, the builders may have intentionally allowed microscopic shifts during seismic activity. Modern earthquake-resistant structures sometimes use flexible base isolation systems based on the same principle. This is especially important because Western Syria sits near active tectonic fault systems connected to the Dead Sea Transform Fault Zone. Historical records describe multiple devastating earthquakes striking the region over the last 2 millennia. Entire cities collapsed. Temples were destroyed. Yet parts of Hosn Suleiman remain standing with remarkable stability. Structural engineers studying the ruins noted that some foundation stones were laid in layered arrangements capable of dispersing vibration rather than concentrating stress at single points. Whether this was intentional or discovered through generations of experimentation remains unknown. Then came the mystery of the stone cutting itself. Several surviving blocks display edges so straight that sunlight still reflects evenly across their surfaces despite centuries of erosion. Tool marks found on some stones suggest repeated abrasion methods rather than simple hammer carving. Researchers believe the builders may have used advanced abrasive cutting techniques involving quartz sand, water, and metal saws or cords. Similar methods were later used by Roman engineers, but some features at Hosn Suleiman may predate the full spread of Roman stoneworking technology in the region. One particularly controversial detail involves right-angle cuts found deep inside narrow structural sections, where workers would have had very limited space to maneuver tools. Reproducing such cuts experimentally using reconstructed ancient equipment proved extremely difficult. Some experimental archaeologists concluded that achieving that level of geometric consistency would require not only skilled labor, but also sophisticated measurement systems capable of maintaining alignment across large stone surfaces. Excavations during the 20th century uncovered another unexpected feature: an elaborate hydraulic management system hidden beneath the visible sanctuary. Small channels carved directly into bedrock controlled rainwater flow across the steep mountain slopes. Their angles were incredibly precise. In some sections, gradients measured only a few degrees, just enough to guide water safely away without eroding the foundations. Modern hydrological studies show that poorly managed runoff is one of the primary causes of ancient mountain structures collapsing over time. Yet Hosn Suleiman's drainage system still functions partially even after centuries of neglect. The sophistication of this water engineering has raised major questions. Roman hydraulic systems are famous for their aqueducts and urban drainage, but Hosn Suleiman demonstrates advanced water control in a remote mountain environment where such precision should have been far more difficult to implement. Some researchers now suspect that local Phoenician or pre-Roman builders possessed a much deeper understanding of terrain hydrology than historians previously believed. As excavations continued, archaeologists uncovered evidence suggesting the complex may not have been purely religious. Thick defensive walls surround parts of the sanctuary. Elevated observation positions provide wide views across surrounding valleys. Certain interior chambers are unusually enclosed and poorly ventilated for ceremonial gatherings. These details led to theories that Hosn Suleiman may have served multiple functions simultaneously: sanctuary, fortress, storage center, and possibly even a protected archive or treasury. The underground sections remain among the greatest mysteries. Ground resonance tests conducted in limited areas produced hollow acoustic responses beneath several floor sections. This suggests the presence of unexcavated chambers or tunnels still sealed beneath the ruins. Similar discoveries at other ancient sites often revealed hidden storage rooms, ritual chambers, or escape passages. But because of political instability and limited archaeological access in Syria over recent decades, large-scale subsurface scanning technologies such as ground-penetrating radar and full 3D mapping have never been comprehensively deployed at the site. That absence of modern surveying technology is significant. At sites like the Egyptian pyramids, scanning projects recently discovered hidden voids previously unknown for thousands of years. At Teotihuacan in Mexico, underground tunnels completely changed understanding of the city's ritual structure. Researchers suspect Hosn Suleiman could contain equally transformative discoveries if extensive imaging were ever conducted. Another mystery lies in the architecture itself. The complex displays a blend of cultural influences that do not fit neatly into a single civilization. Some columns resemble Greco-Roman proportions. Certain foundation techniques appear closer to Phoenician coastal engineering traditions. Meanwhile, geometric layouts in several sections resemble Anatolian ceremonial structures found hundreds of kilometers away. This has led historians to speculate that Hosn Suleiman may have been constructed over multiple eras by different groups sharing engineering knowledge across the eastern Mediterranean. The question becomes even more intriguing when considering trade and cultural exchange during antiquity. The Phoenicians were among the greatest maritime navigators of the ancient world, establishing networks stretching from the Levant to North Africa and Spain. If engineering concepts move through those networks alongside goods and religion, sites like Hosn Suleiman may preserve evidence of technological collaboration long before formal empires unified the region. Perhaps the greatest mystery surrounding Hosn Suleiman is not what has been discovered, but how little of it has been fully studied. Unlike globally famous archaeological sites flooded with international funding and advanced scans, Hosn Suleiman remains relatively isolated from modern archaeological attention. Entire underground sectors may still lie untouched. structural systems that resisted earthquakes for centuries remain poorly understood. Stoneworking methods visible in the ruins continue to challenge assumptions about regional technology levels during antiquity. Do you think Hohensulliman was simply a forgotten sanctuary, or could it be hiding knowledge and engineering techniques far beyond what we currently understand? Share your thoughts in the comments below. Torre de los Escipiones rises beside an ancient Roman road near the Mediterranean coast of Spain, weathered by salt wind, rain, and almost 2,000 years of exposure. Yet the two giant stone figures carved into its surface are still staring outward with details that should have disappeared centuries ago. Archaeologists still debate how the monument survived this long in a coastal environment that destroys stone far faster than this. Even stranger, nobody is completely certain who the figures represent, who was buried inside the tower, or whether it was truly a tomb at all. The monument stands just outside the ancient Roman city of Tarraco, modern Tarragona, once one of the most important capitals of Roman Hispania. It was built beside the Via Augusta, the great imperial road stretching across the Iberian Peninsula. Thousands of travelers, merchants, soldiers, and officials would have passed it constantly. Unlike hidden ruins buried in deserts or jungles, Torre de los Escipiones was designed to be seen. The structure was first documented in detail during the 18th and 19th centuries as scholars began studying Roman remains across Spain. Early historians believed the carved figures represented the famous Scipio brothers, Roman generals linked to the conquest of Hispania during the Punic Wars. That interpretation gave the monument its modern name. But modern archaeology later revealed something unsettling. The identification was almost certainly wrong. The greatest mystery surrounding the tower is not its identity, but its survival. The structure is built from local limestone and sandstone materials that normally erode aggressively in marine climates. Mediterranean coastal air carries salt particles that penetrate porous rock. Over centuries, those salts crystallize within the stone, causing fractures, surface scaling, and gradual collapse. Many Roman ruins across the region suffered catastrophic erosion. Decorative carvings in coastal environments often lose definition within a few centuries. Yet the two towering relief figures on Torre de los Escipiones remain visible after nearly 2 millennia. Their outlines are still recognizable. Folds of clothing remain partially intact. Facial structures, though damaged, can still be studied. This has led researchers into an uncomfortable technical question. Why did this monument survive better than expected? Some archaeologists believe the Romans deliberately selected unusually dense stone containing mineral compositions more resistant to salt crystallization. Others suspect the surface may once have been coated with protective pigments or mineral treatments now mostly invisible to the naked eye. Roman builders were known to experiment with lime compounds, pozzolanic mixtures, and surface finishing methods capable of dramatically increasing durability. At sites across the empire, from aqueducts to harbors, Roman engineering repeatedly demonstrated an understanding of materials far ahead of many later civilizations. Marine Roman concrete has famously survived seawater for 2,000 years, while many modern concretes degrade within decades. Torre de los Escipiones raises a similar possibility on a smaller scale. Perhaps the stone itself was treated using methods no longer fully understood. The mystery becomes even more striking when compared to other ancient relief monuments. The sandstone facades of Petra have suffered massive erosion despite the dry desert climate. Numerous Maya carvings in humid Central America lost fine detail within centuries. Even parts of Roman coastal ruins elsewhere in Spain deteriorated more severely than this tower. Yet the figures here endured relentless humidity, wind, temperature shifts, and sea exposure while remaining recognizable enough to spark debate centuries later. Modern scans of the monument revealed additional anomalies in the construction itself. The tower, roughly 9 meters high, was assembled using carefully cut stone blocks fitted with unusual precision for a relatively small funerary monument. The joints between stones remain remarkably tight. There is little evidence of thick mortar compensating for irregularities. This matters because coastal terrain around Tarragona experiences long-term micro-movements and ground instability caused by moisture cycles and geological settling. Structures built with poor weight distribution gradually crack or lean under such conditions. But Torre de los Escipiones remained standing through Roman collapse, Visigothic occupation, medieval wars, earthquakes, and modern industrial expansion. Some engineers studying Roman masonry suggest the builders used advanced load-balancing principles normally associated with much larger ceremonial structures. Certain internal weight distributions may have reduced stress concentrations throughout the monument. Others speculate hidden stone-locking techniques were employed within the upper sections. The obvious question follows naturally. Why would Roman builders invest such precision into what appears to be a roadside tomb? That question becomes even stranger when examining the carvings themselves. The two giant figures are now believed by many historians not to be Roman generals at all, but representations of Attis, a deity connected to Eastern Mediterranean mystery religions. Attis originated in Phrygian belief systems from Anatolia and later spread through parts of the Roman Empire. The god was associated with death, rebirth, vegetation cycles, and funerary symbolism. If this interpretation is correct, Torre de los Escipiones may represent something far more unusual than a wealthy Roman burial monument. It could be evidence of Eastern cult practices reaching Hispania at a surprisingly early stage. This changes the entire meaning of the structure. Instead of a simple tomb, the tower may have functioned as a symbolic gateway connected to beliefs about rebirth and immortality. The placement beside the Via Augusta becomes more significant under this theory. Travelers entering or leaving Tarraco would encounter a monument linked not only to death, but possibly to spiritual transformation. Roman roads often served political and military purposes, but they also carried religions, rituals, and secret cult traditions across enormous distances. The tower may represent physical evidence of that cultural movement. The interior deepens the mystery further. Archaeological investigations failed to uncover clear human remains definitively linked to the monument. No rich burial chamber was discovered. No massive funerary treasure appeared. No inscription fully explains who commissioned it or who was supposed to rest inside. This absence is difficult to explain because elite Roman funerary monuments often emphasized identity and status. Wealthy families wanted names remembered. They used inscriptions, sculptures, and symbolism to project prestige into eternity. Yet here, the identity at the center of the monument remains almost invisible. One possibility is ancient looting. Tomb robbery was common throughout Roman history. Valuable grave goods were frequently stolen long before modern archaeologists arrived. Another theory proposes the monument functioned primarily as a cenotaph, a symbolic memorial rather than a true burial site. Some historians even suggest its role may have been more ritualistic than funerary. If Eastern cult symbolism truly existed here, the structure may have held ceremonial meaning beyond conventional Roman burial customs. Another major source of debate involves the damaged Latin inscription once carved onto the monument. Only fragments survived. Time erased crucial sections capable of identifying the owner, dedication, or precise function of the tower. Those missing letters created enormous interpretive gaps. Entire historical narratives now depend on incomplete words and broken grammar. This is one of the most frustrating realities in archaeology. Sometimes the disappearance of only a few centimeters of stone can erase the identity of an entire civilization's monument. Excavations and scholarly studies across the 19th and 20th centuries gradually transformed understanding of the site. Early antiquarians mainly focused on visual interpretation, producing sketches and speculative historical connections to the Scipio family. Later archaeological work examined construction techniques, carving styles, and Roman funerary architecture more scientifically. Researchers compared the monument to other Roman mausoleums across Hispania and the Mediterranean world. These studies revealed stylistic influences inconsistent with the original Scipio theory. Archaeologists also documented the monument's structural resilience in detail. Careful surveys showed that despite erosion, much of the core masonry remained exceptionally stable. Stone deterioration patterns suggested selective resistance rather than uniform decay. This fueled further speculation about quarry selection and Roman treatment methods. Each study produced more technical data, yet none fully solved the central mystery of preservation. In recent decades, conservation specialists used modern imaging and restoration analysis to monitor microscopic cracking and mineral weathering. Their findings confirm that the tower continues resisting environmental destruction more effectively than expected. The monument should theoretically display far greater surface loss after centuries of marine exposure. Instead, many critical sculptural features survived long enough for modern researchers to still analyze artistic style and iconography. Deep within the windswept silt of the northeastern Nile Delta lies a ghost of the ancient world, a city that served as the capital of kings, yet vanished so completely it was thought to be a mere myth for millennia. While the Great Pyramids of Giza capture the world's imagination with their geometric perfection, Tanis holds secrets that are far more haunting and visceral. It is a place where granite giants lie shattered in the mud, and where the traditional solar radiance of Egyptian gold was eclipsed by something far more precious and spiritually unsettling, the cold, ethereal shimmer of ancient silver. The story of Tanis is not just a tale of fallen stone, but a narrative of a lost capital that once dictated the fate of the Mediterranean. For centuries, this metropolis was the gateway to the east, a strategic powerhouse and the seat of the 21st and 22nd dynasties. Yet, as the Plusiac branch of the Nile choked with silt and shifted its course, the city was slowly strangled. By the Roman era, the once great metropolis had become a graveyard of broken obelisks. Eventually swallowed by the rising water table and the salt marshes of the delta, the world forgot Tanis existed until 1939, when the French archaeologist Pierre Montet arrived at the site. While the drums of World War II were beating across Europe, Montet was on the verge of a discovery that should have rivaled the finding of Tutankhamun's tomb. However, because his revelations were published as the world descended into total war, his work remained buried in the shadow of global conflict. He didn't just find a city, he uncovered a royal necropolis hidden within the temple precinct, the only place in Egypt where multiple pharaohs were found in their original, undisturbed resting places, protected by the very mud that had hidden them from tomb robbers. The most profound enigma of Tanis is not found in the scale of its ruins, but in the specific choice of metal used to honor its dead. When Montet breached the burial chamber of Pharaoh Susenzthirst, he encountered a sight that defied everything previously understood about Egyptian funerary rites. In a land where gold was traditionally considered the flesh of the gods, Susenz was encased in a magnificent solid silver anthropoid sarcophagus. This was a radical departure from the norm. In ancient Egypt, silver was known as hedge, and because the nation had no natural silver deposits, it had to be imported through arduous and dangerous trade routes from the Near East or the Mediterranean. During the Third Intermediate Period, silver was exponentially more valuable and rarer than gold. To be buried in a solid silver coffin was a display of wealth and resourcefulness that exceeded even the boy king Tutankhamun. The mystery deepens when examining the craftsmanship. The silver coffin is a masterpiece of metallurgy, shaped with such precision that it suggests a level of stability in Tanis that historians previously thought impossible for this era of supposed decline. The question remains, Why did these kings choose the lunar glow of silver over the solar radiance of gold? Some scholars suggest a theological shift toward the moon god Khonsu, while others believe it was a stark demonstration of their absolute control over the world's rarest trade commodities. Beyond the silver, Tanis presents a baffling architectural paradox that has long frustrated Egyptologists. As Montet excavated the Great Temple of Amun, he found massive statues, columns and obelisks bearing the cartouche of Ramesses the Great, a pharaoh who lived and died more than 2 centuries before Tanis ever became a capital. For decades, this led to massive historical confusion, with some early explorers wondering if Ramesses II had built the city himself. The truth eventually revealed a feat of ancient engineering that borders on the impossible. The kings of Tanis did not quarry new stone for their capital. Instead, they literally dismantled the former capital of Pi-Ramesses and transported thousands of tons of granite statues and 200-ton obelisks across the delta to rebuild them in Tanis. It was a recycled city, a grand architectural illusion of power where the past was physically uprooted and replanted to legitimize a new line of kings. This massive relocation of heavy stone across marshland remains one of the most underrated logistical achievements of the ancient world, proving that even in a time of political fragmentation, the Egyptians possessed the technical genius to move mountains. The aura of mystery surrounding Tanis is further amplified by its place in modern mythology and biblical history. Pop culture, most notably the cinematic masterpiece Raiders of the Lost Ark, positioned Tanis as the final resting place of the Ark of the Covenant. According to the legend, the pharaoh Shishak brought the Ark to Tanis after he plundered the Temple of Solomon in Jerusalem, while direct archaeological evidence of the Ark remains elusive. The connection to Shishak is grounded in historical reality. Pharaoh Shoshenq I, the biblical Shishak, reigned from this very city. In the ruins, archaeologists have found evidence of the immense wealth he brought back from his campaigns in the Levant. The mystery lies in what else might be hidden in the unexcavated sectors of the city. If the treasures of Solomon were indeed brought here, they may still lie deep beneath the thick saline mud, a terrain so difficult and corrosive that only an estimated 10% of the city has been properly uncovered. The legacy of Pierre Montet's work at Tanis remains one of the most significant yet overlooked chapters in the history of archaeology. He recovered masks of pure gold, intricate lapis lazuli jewelry, and the silver sarcophagi that gave these rulers the title of the Silver Pharaohs. These finds proved that the so-called Dark Ages of Egypt were actually a period of incredible sophistication and international influence. Today, Tanis remains a haunting and evocative sight. Unlike the polished tourist tracks of Luxor or the Giza Plateau, it is a chaotic field of tumbled giants and half-submerged walls. It stands as a silent, powerful reminder that even the most formidable empires can be erased by a shifting river, leaving only the cold, mysterious glint of silver to tell the story of a forgotten age of kings. The city of Tanis continues to challenge our understanding of Egyptian history, forcing us to look past the gold of the sun and into the silver shadows of the delta. The Senegambian stone circles stretch across the savanna landscapes of modern-day Senegal and the Gambia as one of the least understood megalithic engineering systems on Earth. More than 1,000 stone circles and nearly 30,000 carved monoliths extend across over 100 kilometers of West African terrain. No surviving written language explains who designed them, and no surviving blueprint reveals how they were organized. Yet the precision of their geometry, the scale of their construction, and the engineering hidden beneath the soil suggest a civilization far more sophisticated than historians once believed. The modern world only began to understand the scale of the site during colonial-era surveys in the 19th and early 20th centuries. Early explorers initially assumed the stones were random tribal monuments or simple burial markers, but systematic excavations later revealed something far more complex. Archaeologists uncovered carefully planned circular formations, deep burial chambers, iron artifacts, trade goods, and evidence of long-term construction phases spanning more than 1,000 years. Radiocarbon dating, eventually placed much of the construction between the 3rd century BCE and the 16th century CE, making the system contemporaneous with powerful medieval kingdoms across Africa and Europe. What immediately separates the Senegambian circles from many other ancient monuments is scale. The site contains over 17,000 individual stones in documented zones alone. Some monoliths stand more than 2.5 meters tall and weigh up to 10 tons. Most were carved from laterite, an iron-rich stone that becomes extremely hard after exposure to air. Modern geologists note that laterite is difficult to shape consistently without strong cutting tools because its density changes as it oxidizes, yet thousands of these stones display remarkably similar cylindrical forms. This raises one of the oldest mysteries surrounding the site. How were these stones quarried and shaped with such consistency? Unlike Egypt or Rome, there is no evidence of large-scale surviving machinery, advanced pulley systems, or extensive metal workshops associated with the circles. Iron tools existed in West Africa during this period, but archaeologists still debate whether the available metallurgy was sufficient to mass-produce monoliths with this degree of uniformity. Some stones show flattened surfaces and symmetrical shaping that appear intentional rather than naturally fractured. Even more puzzling, several quarries identified near the site are located kilometers away from the final construction zones. Transporting stones weighing multiple tons across unstable seasonal terrain would have required enormous coordination. During the rainy season, much of the region becomes muddy and difficult to traverse. Without paved roads or evidence of wheeled transport systems on a large scale, researchers believe labor crews may have relied on sledges, wooden rollers, or compacted earthen pathways. But no direct physical evidence survives to fully confirm the methods used. But the greatest mystery may lie not in the stones themselves, but in their geometry. Across multiple sites including Wasu, Sine Ngayen, and Wana, the circles display astonishing dimensional consistency. Many measure between 4 and 6 meters in diameter with nearly equal spacing between individual monoliths. In some formations, deviations between stone intervals are minimal, despite the monuments being built centuries apart. Archaeologists were stunned by how standardized many of these circles appeared. Such consistency suggests the builders used repeatable measuring systems rather than visual estimation alone. Some researchers propose that the engineers may have employed central stake and rope techniques similar to methods believed to have been used at Stonehenge. By anchoring a fixed pivot point and rotating a measured cord around it, ancient builders could theoretically produce near-perfect circles over large construction areas. Yet the precision seen at Senegambia goes beyond rough ceremonial geometry. Several circles maintain highly balanced spatial proportions even after partial collapse. In some cases, the orientation of entrance stones appears deliberately aligned relative to neighboring formations. Statistical studies conducted on certain clusters suggest the placements are unlikely to be entirely random. This has led some researchers to question whether the builders possessed a more advanced geometric tradition than previously assumed for the region. What makes this especially controversial is the absence of surviving educational infrastructure. No mathematical tablets, no engineering diagrams, and no carved measurement scales have ever been discovered. And yet, the circles repeatedly demonstrate evidence of organized planning. Comparisons with other megalithic cultures only deepen the mystery. At Stonehenge, researchers found evidence of astronomical alignments tied to the solstices. In ancient Egypt, geometric planning was linked to centralized state bureaucracy and written mathematics. But in Senegambia, the engineering appears disconnected from the kinds of administrative systems historians normally associate with monumental architecture. There are no giant palaces nearby, no massive urban ruins, and no royal inscriptions claiming ownership. Instead, The circles seem to emerge from a decentralized culture capable of organizing labor across generations, without leaving behind the bureaucratic fingerprints normally expected from large engineering projects. Even more mysterious is how the stones were erected. Many monoliths remain almost perfectly vertical despite centuries of erosion, flooding, and shifting ground pressure. Excavations revealed that some stones were buried deep underground at carefully calculated depths that helped stabilize their center of gravity. Engineers studying the foundations found that several circles used surprisingly effective weight distribution techniques. The deeper foundation pits prevented tilting even in water-saturated soil conditions. For a civilization with no surviving mathematical texts, the structural understanding demonstrated here is extraordinary. Some of the strangest stones add another layer of uncertainty. At several sites, archaeologists discovered rare bifurcated stones shaped almost like the letter Y. These monoliths are extremely unusual within African megalithic traditions. Unlike ordinary standing stones, they appear intentionally sculpted into branching forms. Their function remains unknown. Some theories suggest they served as symbolic markers tied to elite burials or ritual status, while others speculate they may have represented cosmological ideas or clan identities. But manufacturing such shapes from brittle laterite would have required careful control during carving. A single mistake could fracture the entire stone. The fact that multiple examples survive suggests the builders possessed specialized stoneworking knowledge that has since disappeared. Beneath many circles, archaeologists uncovered complex burial systems containing iron weapons, copper ornaments, ceramics, and glass beads imported through trans-Saharan trade routes. Chemical analysis of certain beads indicates links to North Africa and possibly the Middle East. This suggests the civilization responsible for the circles was not isolated, but connected to larger economic networks spanning thousands of kilometers. And yet, despite evidence of trade sophistication, the society itself remains strangely invisible in the archaeological record. No confirmed capital city has been identified, no surviving chronicles describe the builders directly, and no clear ethnic continuity has been definitively established. It is as if the engineering survived longer than the identity of the people who created it. Some researchers also suspect the circles may contain astronomical significance. Certain formations appear oriented towards seasonal solar positions associated with rainfall cycles critical for agriculture. In a region heavily dependent on predictable monsoon timing, even basic solar observation could have carried enormous practical value. However, unlike the clearer solar alignments documented at Stonehenge or Newgrange, the astronomical evidence in Senegambia remains disputed. Critics argue many alignments may simply result from pattern recognition imposed by modern observers. Still, the repeated directional similarities between multiple circles continue to fuel debate. Perhaps the most unsettling aspect of the Senegambian circles is not what archaeologists have discovered, but what they have not. To quarry tens of thousands of stones, to transport them across difficult terrain, to standardize their geometry, to organize labor over centuries, and to preserve structural stability in tropical conditions, all without leaving behind a conventional historical record, suggests the existence of a sophisticated organizational system that history barely remembers. What do you think these mysterious stone circles were truly built for? Were they purely ceremonial burial sites, or evidence of a lost engineering tradition far more advanced than historians realize? Share your thoughts and theories in the comments below.